Please take a seat in the back because we're ready to start this Tuesday morning session. I'm not one of the organizers. Many of you don't know me. I am Michele Benzi. I am professor of numerical analysis at the Scuola Normale Superiore, and I've been asked to chair this morning session, which is primarily devoted to numerical and computational aspects. I'm pleased to introduce the first speaker, Gabriel Peyré, who is at CNRS and the École Normale Supérieure, which, as you know, is the Parisian branch of the Scuola Normale Superiore.
Always a pleasure to come to the Italian branch. So thanks a lot for the invitation. It's always a pleasure to be here. So I'd like to take this opportunity to make this what I call the unbalanced tour. So as the name suggests, it's going to be focused on unbalanced optimal transport with more or less a computational perspective on it, and see what it brings for machine learning typical application. Why I think it's kind of a fundamental tool or a key ideas if you want to do optimal transport for practical applications. Maybe first, we'd like to highlight some what I call curse and blessing, but some difficulties that you might face and what are the workaround. What first come to mind, of course, is the computational aspect. The fact that typical simplex algorithm will roughly scale like cubic in time, which is already quite a lot. But in fact, what is probably even more problematic, and really, I think we would be hitting a wall in practice if we would not do something else, is the fact that in high dimension, you will be facing the curse of dimensionality when discretizing optimal transport problem, meaning that the number of samples that you would need to take to even just approximate distances, I'm not even speaking about applying to some problem, just like computing the distances, will scale exponentially with the dimension. And one solution to this, which we have already seen yesterday, a lot of talk about this, is entropic regularization or Schrödinger problem, which I'd like to explain at least briefly. The second aspect, which is probably even more important, or at least as important, is what could be called lack of stabilities. Basically, the fact that you impose exact conservation of mass leads to numerous difficulties. One aspect that was studied in details, among others by Lénaïc, Chizat, is the fact that Wasserstein flows have difficulties. Many functional are not displacement convex. And in practice in machine learning, all the functional you would encounter, they are not displacement convex. What can you do? I mean, somehow to alleviate these difficulties of convergence. Also very related to this, in fact, it's just two sides of the same problem, is the fact that optimal transport is very sensitive to outlier or noise, because you really want exact conservation of mass. If you have some outliers or some noise, you would basically have a non-smooth transportation map, which might be problematic in many scenarios. One solution to this, maybe, I mean, the canonical solution is to do this idea of unbalanced optimal transport that I would explain. And one last aspect that would at least to speak a bit, because it leads to many open problems, and basically everything is open on this side, is how do you do if you don't really know the cost? How do you do metric learning in some sense? How do you infer some cost between two different spaces? What should be the properties of this cost? Can you study this type of cost? And you can frame this into the language of Gromov-Wasserstein, which is a nice extension of classical optimal transport. Okay, so basically this idea of unbalanced optimal transport is not new. Maybe I would say the first one to really stress this is a really nice paper, maybe not so well known by Jean-David. Of course, this has nothing to do, I mean, at least to the best of my knowledge, Jan was not involved in it, but of course, this is the Benamou-Brenier geodesic, but this work is only made by Jean-David. And he makes the remark, as I say, that typically you'd like to relax the conservation of mass constraint. And what Jean-David proposed is simply to do an Inf convolution between optimal transport distance and Euclidean distance, which is what he has proposed here. This is very nice, but the downside of it is you impose a strong constraint on the marginal because you compare them using a L2 functionals, which means that the marginal has to density with respect to Lebesgue or with respect to some fixed distribution. So I would say the second step in this direction was done among others by Liero, Milke, and Savare in a landmark paper, which is the idea that instead of comparing the density using some fixed Euclidean distance, you'd rather like to use the comparison of relative densities toward one in some sense. And a way to do this is to use, for instance, the relative entropy. So in my talk, KL, the Kullback-Leibler divergence, refers to the relative entropy. It's just normalized to be always positive, to always be a distance-like functional for any positive measure. Okay, so usually you don't have this term, But since here you want to compare a distribution which are not unit mass, you need to add this. So basically here you see that you have the usual Kantorovich primal functional, but what you do is instead of requiring exact conservation of mass, so instead of requiring that the first marginal of pi is exactly equal to the input alpha, you just penalize it in some sense. And the way you penalize it, you have various ways to do this. So Jean-David was using the L2 norm. Here it's using the relative entropy, which is a very natural functional, both in terms of theory, as I would explain now, but also in terms of numerics. It really leads to very simple algorithm. Okay, and here, on purpose, I have introduced a relaxation parameter tau. So somehow if tau goes to infinity, you recover exact conservation of mass. So you recover classical optimal transport, balanced optimal transport. And as tau goes to 0, you relax more and more, and you allow for mass variation. Okay, so tau is some kind of a penalty that you can play on to trade transportation versus creation or destruction of mass. Okay, and this is and what you can say about it, it's like it conserves some properties of usual optimal transport. For instance, it's a distance on the cone of positive measures, and it metrizes the weak convergences. And in practice, so this is a very typical scenario. Here what I do is I take two mixtures of Gaussian, so the red and the blue, and I want to do optimal transport between the two. But I've done on purpose a slight modification of the mode so that you see this first red bump has a little bit more mass than the second one. So what optimal transport would do is that it would split the first Gaussian and spread it into the two blue bump, which is typically what happens in practice. You never have exact balancedness of the modes. So this is a typical, I would say, real-life behaviors. And it typically leads to a non-smooth transportation map, okay, which is this purple here lines, okay. You see that because it needs to send mass very far away, the transportation mass is very irregular. So now what you would do is you would slightly decay the value of tau, and what you would have is that you don't exactly ask for exact conservation of mass. So what I display here in blue and red are the marginal P1 and P2. So you can really interpret this process as a two-step process. It first reduces or augments a bit the mass, and then it do traditional optimal transport between P1 and P2. So you see what happened is now the two bumps have exactly the same height, so the same mass. And now it can do just a usual optimal transport, which in this case is just going to be locally a translation. Okay, so by playing on the tau value, if you want, what you obtain is a very smooth transportation map, at the price of course, modifying a bit the input. But what is nice is that it's done automatically. You don't need to do a pre-processing. Because of course, if you get 20 modes, no way you could like play on each mode independently and modify the mass independently. So really this method will do this automatically for you. It will modify locally the modes and then do, I would say, a nice transportation. Of course, there is no free lunch. If you decay too much the value of tau, then weird things will happen. You will destroy too much the mass. And typically, I don't know if this has been analyzed theoretically, but you see some slight shift in the position of the modes, which means that now the translation is not anymore very well estimated. So I would say there is a sweet spot that here is somehow between 10 to the minus 1 and 1, where you do a nice balance of the mode, but you don't destroy too much mass, and then things go well. So you see there is, of course, a very important problem, which is parameter selection. I would not enter this area. It's, of course, very important in machine learning to do typically cross-validation or to have some data on which you can somehow select the best tau, and then it would lead to, I would say, improvement in practice. There is also, I would say, a geodesic side of this story, which was also very nicely explained in the same paper. We also work on this with Lénaïc, and there is also a very related work by Léonard Mont-Saint-Jean, actually the same formula. So there are 3 teams that work on very similar things. And for this, it's quite surprising. If you want to maintain the geodesic structure of W2, you cannot use the same cost. You need to change a bit the cost. And it turned out that the only way to modify this is maybe a little weird, is to take minus the logarithm of the cosinus of your distance. Okay, I will not enter the details of why you need to do this, but it has a crucial aspect, is that now this new cost that you need to use has a cutoff. You see that this cost blows, basically, if x minus y is somehow larger than something proportional to tau, this cost becomes plus infinity. And this is really a crucial thing. If you want to be a geodesic, maybe you don't want to be geodesic, but if you want to be geodesics, you cannot transport mass infinitely far away. At some point, you need to pay a price that is infinite, and instead of transporting, you need to kill your particles. Okay, and this is one of the surprising aspects of this theory of Liro-Milke-Savary. But if you take exactly this cost, you can in fact show that this distance is equivalent to a Benhamou-Brenier type geodesic formulation, where you get the classical cost that you need to pay for transporting according to a vector field V, but you also get an extra cost that you need to pay if you want to kill particles, basically if you want to have a source term that creates or destroys particles. Okay, so you see here, it's like hybridation or a mixing between two metrics, an horizontal metric which displays the point, and a vertical metric that can create or destroy mass. Okay, and you can show that it's actually equivalent to this static formulation. And this is, I would say, the geodesic or the McCann interpolation, but this time it's a McCann interpolation over both position and elevation. And you see exactly the same phenomena as before, but now it's dynamic. If tau goes to plus infinity, you get this little soliton, which is due to the fact that the transportation is not regular. If tau is like 0.1, you get a very nice interpolation, where you get both translation of the mode, but at the same time, you get slightly decay of the amplitude. You see this very nice interpolation. And you can show, it's quite easy to do the computation, that if tau goes to 0, you actually recover the Hellinger distance. So very similar to Jean-David, except you need to take the square root of the density before computing the Euclidean distance, which exactly comes from this penalty here. So in fact, the Hellinger distance is, I would say, the canonical geodesic structure on measure if you don't want to do optimal transport. And of course, here you get teleportation of mass, you just get like linear blending in some sense. So, well, I mean, these are different types of geodesics on the cone of positive measures. So what can you do with it in practice? I would say that the first step, or one, I mean, striking application, is to try to study a classical optimization method view as particle systems, as pioneer among others by Lénaïc, which is this idea that there are many problems in machine learning or in image processing that can be recast as optimization over some measure. You want to minimize some function of a measure here. And a way to discretize this, of course, is to discretize the measure, right? I mean, that's absolutely the first way to do it, where you would discretize the measure by introducing both position and weight and amplitude, okay? What you can do is only do translation, modification of the position, only optimize on the x variable, and this is, of course, equivalent to doing a Wasserstein flow. So here I'm assuming everything is regular, so I'm assuming the function is very nice, and you can do all the computation. In particular, it is smooth with respect to the position. So it's either a GKO flow or a particular flow or just a PDE on the densities. And here you're only moving around the position. One difficulty is there's many functional, including perfectly nice convex functional F, that are not geodesically convex, so for which you would actually expect that this type of flow would be blocked in a local minima. A workaround or a way to introduce a bit more flexibility, which makes a lot of sense, of course, is to play not only on the position, but also on the elevation A, okay? So you do the gradient descent on the position, but at the same time, you do the gradient descent on the amplitude A. And the key question, or a nice question, is what type of metric should you put on the couple XA? And the simplest move, or the simplest metric you could think of, if you want to preserve positivity of the measure, is to just use the L2 metric on the position X, and use what is often called the Fisher metric, or the mirror descent metric, which simply you multiply the gradient by the value of the density itself. And you see this really act as a barrier function, but because if A becomes too small, then the movement will become smaller and smaller, and you can never become negative. So in some sense, it's a very natural move to do if you want to preserve positivity. And you can show that this is exactly equivalent to unbalanced optimal transport flow, according to the metric I've defined before. Namely that if you do a GKO method, but you replace W2 by unbalanced optimal transport, this is simply equivalent to also moving the amplitudes according to the Fisher metric. And this is the type of PDE you have, exactly as before in the Benhamou-Brenier formula, where you also get a source term that depend on the functional. Okay, so you see, you move the position, but you also scale the particle size. And this leads to very, very different flow. It looks like both are the same, but because you also move the amplitude, and because the function depends on the amplitude, the flow becomes very, very different. Okay? What can you do with it? A typical example is to apply it to an image processing problem where you want to do super resolution, namely that what you observe is actually a blurred version. Here is, for instance, a Gaussian convolution of some unknown source beta you want to recover. This is typically a problem you would encounter in astrophysics, in seismic imaging or in neuroscience when you want to recover spikes. So there's many problems that you can frame as a deconvolution problem. And what you can do is just a least square fittings. You want to find the best measure alpha that once convolved with your filter, you recover the observation. It's one of the most difficult problems to solve. It's super ill posed because convolving with a filter that is low pass, like a Gaussian, is crazy difficult. So really you want to go back from this to this. So what you can do is typically a Wasserstein flow. And the issue is, of course, this function is a least square, so it's convex in the usual sense, but it's not geodesically convex. So the typical evolutions that you get are very ill posed. Here, maybe after a very long time, because this is like 1 million iteration actually, you would end up maybe converging to the blue point. It's not so clear here whether it's actually blocked in the local minima, but you never see a convergence. It's really too slow. Like these particles, they almost don't move. So actually, I'm not sure it's a local minima or just it didn't converge. But if you do the same with an unbalanced optimal transport, then convergence is much faster. And in fact, you can prove, and it was proved by Lénaïc, Chizat, and Francis Bach, that if your initialization have enough particles everywhere, so typically you are on the torus and you put mass everywhere, you actually never blocked. So typically you would converge to the global minimizer. At least if you assume you converge to something, all subsequences that would converge, they would converge to the global minimizer. Another striking application, which I think was the motivation of Lénaïc, is actually to study even more difficult problem in higher dimension, which is training of neural networks. Training many layer neural networks with many layers is very difficult to understand. And here's just the simplest case where it's a neural network with 2 layers. So this is displayed here. You get your input, Z. Then you multiply by a matrix, denoted as X1. Then you apply a nonlinearity. And of course, it's crucial to have a nonlinearity so that things are really nonlinear. And then you multiply by another matrix to get a real number Y. Okay, so the formula is this. It's just the sum over the different neurons. And the key insight, it's actually very old. If you look at all papers by Andrew Baron, for instance, it was really expressed like this, is to think about a neural network as just a measure over the space of neurons. Okay, so you represent your set of neurons by a measure, because really the weak topology is really the natural one when you want to think about training neural networks. So you represent your neural network using a measure. Each neuron is a Dirac. And then you typically interpret the sum as an integral. It's a tool, for instance, to study what happens when you have more and more neurons, because as you might know, the famous theorem by Sibenko tells you that if you get enough neurons, you can approximate any function. So it's a nice setup to think about the limit, where instead of having a discrete number of neurons, you could even have a continuous number of neurons. Okay? Then you can simply do a least square. Okay? You have some data, Z and Y, and you want to minimize the error you make in a least square sense. In fact, it's exactly at the previous example. It's a linear least square over the space of measure. So it's exactly the same type of problem that you have with Gaussian deconvolution, except here it's in very high dimension, but it's exactly the same problem. You might end up converging to a local minima if you just train your measure classically. So you might think we are hitting a wall, but in fact there is a very nice remark that was once again made by Lénaïc. I guess it was known much before, but it's the first time I've seen this very cleanly. If you use what people would use in practice, which is the Relu nonlinearity. So all neural networks nowadays, they are not anymore trained with sigmoids. They are more or less always trained with a variant of the Relu functional, which is just this one homogeneous functional here. It's very nice because the function is positively one homogeneous, which means that you can project your 2 matrices on the sphere. Okay, you can do this very simple change of variable where you project x on the sphere, and because you see that x appears here and here, it's 2 homogeneous, you would have a x square that would appear in front as a weight here. So what I mean is that the function f is exactly equal to the function f here, where you replace the 1 over n weight by the square of the weight in front. And what you can show, it's quite easy to do the computation. If you do the gradient descent on this side here, it's going to be, of course, a Wasserstein flow. But this Wasserstein flow is exactly equivalent to doing an unbalanced flow, but this time on this new measure that has been projected on the sphere. So classical training of neural network is exactly balanced training of neural networks on the Euclidean space is equivalent to unbalanced training on the sphere, which is nice because it means the algorithm that everybody will use are actually doing unbalanced optimal transport without knowing they actually do unbalanced optimal transport. And somehow an informal theorem, because there's many details that I put under the carpet. In particular, the problem is that the Relu function is non-smooth at 0, so it's not trivial to handle it, is that with the same reasoning as before, you can show that training a Relu network with 2 layers would converge to a global minimum if you get enough Dirac. Of course, it's not a quantitative statement. It requires you to have mass everywhere, so somehow you need to have enough Dirac. And studying how many Dirac you need is probably super hard, because in fact, training a neural network to optimality is known to be typically an NP-hard problem. So you don't expect to be able to prove this theorem with n that is like polynomial in the parameter of the problems. But still, it's a beautiful result that really explains in practice why training a Rayleigh network is actually quite an easy problem, at least if you only care about computing it to global optimality. Let me now come back to, I would say, just classical computation of optimal transport, not gradient flow. I could spend maybe 1 hour speaking about gradient flow, but maybe we need to move forward to a different type of issues. The first thing that I've mentioned is in practice, if you are in high dimension, you would be facing difficulties in terms of algorithm would be slow and curse of dimensionality. And the workaround for this is to introduce entropic regularization. This was championed by Marco Cuturi, who was really the first that explained the benefits of entropy for learning and also for the computational side. And it simply amounts to penalizing the Kantorovich problem, or here the unbalanced Kantorovich problem with the Kullback-Leibler penalty. Okay, I will not really insist on this. There was many talk yesterday, but there is many benefit out of it. The first one is it would smooth the transport plan. It would lead to a transport plan that is smoother. So for instance, here I display, here is for balanced optimal transport. I display a little segment each time an entry in the transportation matrix is slightly larger than 0, so larger than 10 to the minus 3. And you see that as smoothing increases, as the temperature epsilon increases, you're going to connect more and more points together. This will really increase the stability of the solution. For instance, you can show that the transport plan P depends in a very smooth way with respect to the input, so with respect to alpha and the cost. So if you get some noise, it would be beneficial. It's also important because in high dimension, stability is the key to lower the cursor of dimensionality, the sample complexity. And it's also useful if you want to use optimal transport to train neural network. Maybe Marco would say a few words about this, but this leads to smooth loss functionals that you can do gradient descent on them, and things would be working nicely. So there's many benefits of this approach. Maybe, of course, the first benefit is synchron algorithm that was explained in detail in many talks, including Guillaume's, I think, that explained this in these words. Also, Simone explained exactly the same equation. I think the best way, if you're a mathematician, to think about synchron is to think about the dual problem. So here I wrote the dual for the unbalanced optimal transport. It's almost the same dual as before, but basically unbalanced optimal transport on the primal is the same as asking that the dual variable need to be bounded, or at least to control the norm of the dual variable. So meaning instead of having a linear function here, you get a nonlinear exponential function that prevents the dual variable from being too large. But you see what happens if tau goes to infinity, then this just becomes a linear function and you recover classical optimal transport. So it's a slight variation, I would say, on classical optimal transport. The key tools to study this dual problem is to do alternate minimization, to basically write one function f as optimal f as a function of g. And to do this, a nice way to do this is to introduce the soft min operator, which is basically the log sum x functional but rescale by minus epsilon. So as epsilon goes to 0, you somehow doing the you're computing the minimum on the support of alpha. So it's like a smooth version of the minimum operator of a function. And then you can introduce soft C transform, denoted as Simone, I think, so I use the same notation, where you simply compute the C transform, but you replace the minimum by the soft minimum, okay? If I were to do a balanced optimal transport, then for a fixed f, this soft C transform would be the optimal g. And synchron would just be like alternating between the two. What is nice is you can redo exactly the same computation as Simone did yesterday, but I will not do it. It's a good exercise for you to do it, to recover that you get almost the same functional, the same equation as before, except now you need to scale the C transform by this factor, tau divided by epsilon plus tau. So it leads exactly to the same synchron algorithm, but if you want to be unbalanced, the trick is you need at each iteration to just multiply the update by some scalar which is strictly less than 1. Okay, and you see once again what happens when tau goes to infinity, then this scalar tends to 1 and you recover balanced synchron. So doing unbalanced is as easy as simply at each iteration somehow contracting a bit the potential so that they don't become too large. And this amount of contraction will be equivalent to destroying or creating mass. Okay, and then you get all the same theory. So really everything you like or dislike about synchron extend to this unbalanced setting, in particular proof of convergence. So it's a question for Simone. I don't know where is Simone to extend his theorem of yesterday to unbalanced. You have 20 minutes for this, and then you ask your question. But at least you can ask, you can do simpler analysis because Simone did a very complicated, quite involved analysis, but it's a simpler analysis is just use your favorite theorems from convex analysis 101 and to apply it to show 1 over T convergence rate, which is already quite nice, and to see that the number of iterates you need to compute the solution at precision delta is n squared divided by delta square. So it's either good or bad, because in terms of n, it's quite good, n square is not so huge. But in terms of delta, of course, if you want delta to be very small, then you would need tons of iterations. So it's really always the same trade-off with sync-on, which is very good in terms of n, but quite bad in terms of precision. If your goal in life is to go to high precision, don't use sync-on, but I think it should not be your goal in life, so we are on the safe side. What is, I would say, one of the most striking applications, and Philippe Rigollet was in the team working on this, so you might want to ask him a question if you want to know more, but it's a beautiful result by Schimbinger and collaborator, which is like an embodiment of the theory of Waddington, which is very old, of the idea that cells in your body, they evolve during life, when you are a baby and so on, to differentiate themselves and being more and more complicated. And the goal now is to compute this and to see how cells evolve. So in fact, it's displayed at a 2D plot, but it's supposed to be a very high dimensional plot, where each point here, each Dirac, if you want, is actually a cell of your organism, displayed in a space of genes. What you measure is what is called single-cell genomics. It's a revolution in biology, where you can measure the expression of your genes, okay, in terms of gene expression. So it's like a vector in a very high, like 10 to the power 3 dimension. And here, it's actually not a single measure. It's actually several measures, several sets of Dirac that evolves, a bit like a gradient flow. And actually, I think it's a good interpretation, at least metaphorically, to think about life evolution as a Wasserstein flow in the space of genes. And the key question that biologists are asking is to try to understand the trajectory of the cells. Like if you take this cell, which has been differentiated to be very complicated, where does it come from during the life? And the problem is when you do this biopsy, you destroy the cells. So for me, this is really the canonical example of Schrödinger problem in real life. You observe a group of cells at different points in time, and you want to understand the most likely trajectory. So Schrödinger problem was an experiment in his mind, but now we want to do this in practice. And the way people do this, or at least Schimbinger and his team do this, is by solving a sequence of unbalanced optimal transport. I'm not sure it's really coming from first principle, but at least it makes sense that you want to do optimal transport because cells want to do a least effort, and at the same time you want to do unbalance because some cells will be destroyed, some cells will be created, so you don't really want to keep exact conservation of mass. And you do this, and then you can do trajectory inference in a very nice way, and there is a lot of papers now that are building on this idea, a recent paper by Marco and Charlotte Brunn that do this, but this time using gradient flow. So it's, for me, it's one of the most exciting areas of application of optimal transport outside deep learning. Another thing that I want to mention, I will not speak about this in details, but this idea that I've mentioned of the curse of dimensionality, which was championed by the first theorem by Richard Dudley, but there's many follow-up work, which typically says that if instead of having directly access to some continuous density here, you have access to a discrete realization where each point is drawn independently. The typical error on average that you would do if you want to do an error of delta is going to grow like 1 over delta over the dimension. And this is really a sharp result. You cannot really beat this result. Any type of estimator that you would try to build will be facing this wall. So it would really mean that if you have no other insight about what is beta, if you don't know it's a Gaussian or whatever, you just know it's like a density, you can never compute optimal transport. You can never really use optimal transport in high dimension. One counterpart to this, which was proved by Ojodve during our PhD thesis, and it was extended by Thibault Séjourné recently to the unbalanced case, is if you want to do this, but not this time with the true Wasserstein, or the limit when epsilon goes to 0, but with the cost according to Schrödinger, the number of samples you need is going to grow only like 1 over delta to the square, which is exactly the type of non-parametric rates you get in Monte Carlo method. So in some sense, you should interpret this as sync-on is a bit like Monte Carlo method for optimal transport. If you do Monte Carlo to estimate integral, you would get exactly this rate. Of course, optimal transport is more complicated than just computing an integral, because you need to solve an optimization problem, but really the insight is exactly the same as Monte Carlo. Sync-on gives you access to 1 over delta square rate because it's smoothing everything, and it's leading to integrals instead of just having hard constraints. And this is a good side of the story, but as in every story, there is also a bad side. So in some sense, there is no free lunch, because you know this, you cannot beat this. So you cannot use syncorn to try to estimate without the curse of dimensionality optimal transports. If you select epsilon too small, because if you want high precision, you will need to take epsilon too small, of course the constant you have in front will explode. I think it's like in every nice Monte Carlo story, the bad side of the story is usually the constant is fairly large. And here you see the constant will blow like 1/epsilon to the dimension. So typically, if you want to estimate the unregularized quantities, you will need to take epsilon that would scale like 1/n to some power. And if you do the computation, you would recover exactly this curse of dimensionality. Okay, so the take-home message is syncorn is not a way to cure the curse of dimensionality for optimal transport. Syncorn is defining a new type of metric. And I know we all love to study epsilon goes to 0, including myself. I've done my fair share of paper, including with Guillaume and collaborators, to study the limit when epsilon goes to 0. But in practice, in machine learning, you never want to take epsilon too small. So I think the next frontier is not to study epsilon super small, is to take any epsilon you like and to study the property of this metric as being an alternative for optimal transport. Okay, I think it's probably a very important thing to remember is in practice, nobody would use epsilon too small because the algorithm will be too slow. You would be eating the curse of dimensionality. And also maybe you'd like to do some diffusion because you have noise, error, and so on. So okay, end of the parenthesis, but I think it's a nice result, but it's only scratching the surface of what we should be focusing on. Now I would like to conclude with more open problems. Well, I already stated a few open problems, but then here everything would be open problems that you can take home and work. And this problem has to do with metric learning in some sense. How can you do optimal transports between two different spaces for which they belong to maybe two Euclidean spaces of different dimension, and there's no way you can really relate them easily together. So you'd like to have some intrinsic notion of optimal transport across spaces. A good machinery to do this is to say that your data would be modeled as a metric measure space, which means that actually the space itself carries information and you want to take care of this information. Okay, so it's like a triplet where there is a space, a measure, and a distance, typically satisfying the triangular inequality on this space. And one key idea was introduced almost independently by Carter Dorsturm and Facundo Memoli almost 10 years ago, which is this idea that instead of doing a cost that will depend only on single particles, you have X, it moves to Y, and you just measure the cost of transport. Here you would rather look at some isometry principle. And instead of looking at the single particles, now you look at pairs of particles, X and X prime. They are mapped by a transport map or a coupling to Y and Y prime. And now you measure the default of isometry. Okay, maybe you could cook other costs. I think it's a very, very interesting and stimulating question to look at interesting costs. But probably the simplest one is to look at pairs of particles and to do just a least square on the induced distance. And now you just simply integrate twice this kernel. So remember now it's a kernel of 4 variables against the tensor product of pi to itself. What does it mean somehow is if pi xy, x prime, sorry, pi xy and pi x prime, y prime are having a large cost for a large value, sorry, for pi, you multiply them together. It's really a way to describe the fact that you're going to transfer this pair to this pair. And you sum up to get the total isometric cost. Okay, so it's rather nice. I mean, or not nice. Maybe I should first say what it's nice. It's nice because it induces some kind of a distance up to isometry, because it's easy to see that this quantity is 0 if and only if the two metric measure spaces are isometric, meaning that there is an isometry between the two spaces that push forward alpha to beta. Okay, so up to this isometry, it's like inducing a metric on the space of metric measure space. You could do, for instance, gradient flow has been studied by Carter Dorsturm. You can do a lot of things that have been explained by Facundo Memoli. But of course, the key bottleneck is how can you do the computation? And the difficulty is that this function is not anymore a linear function, it's a quadratic function. And the bad news is it's non-convex. I think you should expect that this type of functional should be non-convex, because if you get a space with discrete symmetries, like if it has a symmetries, you expect this type of functional to have two global minimizer, but that's it. So you expect this functional to be highly non-convex, otherwise it will not be doing a good job. So this is to be expected that it's non-convex. In fact, in some cases, it's non-convex, but not so nasty. I think an iconic case is if you take the space to be Euclidean, even of different dimension, you can easily show that this function is actually concave. So what you are actually minimizing in this type of problems over Euclidean space is actually minimizing a concave function. So you would expect somehow that the solution should be closed, or I mean, having some kind of a Monge map structure, because if you do over discrete points, two space with the same number of points with uniform measure, then the solution will be a permutation.
So I think there is some regularity or something you could say. There is a recent paper by François-Xavier Vialard and his collaborator, maybe this week actually on arXiv, that actually studies this case, and you can show in the Euclidean space if you put a square here. So if you take Euclidean distance to the power 2, and then you redo a power 2, you can show that unless you are very, very unlucky, so there is a description of what it means to be unlucky, but you would have a Monge map, for instance. But everything else is totally open. So it's typically a concave minimization problem over the space of transportation coupling. What are the applications? So it's non-convex, but of course you can try algorithm on it. With the first class of application, it's already a long time ago by Facundo and others, is to do shape matching. You could do shape matching between two surfaces, for instance, endowed by their geodesic distance. You want to do a matching that respects the geodesic distance. You could also do matching between shapes of different dimension, of course, because, well, you can do it. But I would say a more interesting application, it was like, if you want, an alternative or an extension to this work by Schibinger, it's not the same problem, of course, is to do single-cell multi-omics integration, which is one of the most challenging and important thing in biology recently, is the idea that you want to do this idea of single-cell genomics to record the information of cells, but usually you will record the information on cells using different devices. You get different type of information. Could be, for instance, here, depending on the gene expression activity. You could also have some protein information. Here it's what is called chromatin accessibility. So you get around 5 or 6 different type of modalities. But unfortunately, each time you do a biopsy, you would kill the cells. So it's exactly the Schrödinger problem, but now it's Schrödinger problem between 2 different spaces. So in some sense, a good way to describe the problem is Gromov-Wasserstein. You get the same measure, but view over 2 different metric space in some sense, and you want to register them together. There is a nice paper, they call this Scott algorithm by Demichi and collaborator, which is exactly applying optimal transport. And what was very nice is a few months later, we released on arXiv with Thibault a paper extending unbalanced optimal transport, Gromov-Wasserstein to the unbalanced case, and they actually use our code to extend this to the unbalanced setting. So maybe I could spend a few minutes, a few seconds or minutes to describe it. Before, maybe I would say a few words about the problem, so the algorithm that you would use before speaking about unbalanced optimal transport. I would say the first thing when you have this type of non-convex optimization problem is to look at first order optimality condition, and you can easily show that you are actually an optimal plan for the Gromov-Wasserstein functional if and only if the linearized cost, so if you compute the gradient or the derivative of the quadratic function, it gives you a cost. This is exactly just the gradient derivative of the quadratic function. So you integrate the kernel, but only on the 2 last variables. This gives you a cost. But this cost now is not anymore the squared Euclidean cost. It's a weird cost parameterized by your coupling. And you can show that you solve Gromov-Wasserstein. It implies that you're going to solve an optimal transport problem between 2 spaces according to this cost. So you see really the key issue or one key problem if you want to show existence of Monge map or things like this is to understand the property of this cost. So for instance, it's the recent work of François-Xavier, for instance, Vialard, that in the simplest case where you take this k to be the one before here, but when you put a square here and you consider Euclidean space, you can show that in some case it satisfies the twist condition. And you can thus infer that you would have existence of a Monge map. But besides this trivial, a bit degenerate case, I think everything is open regarding existence of Monge map, or at least some properties that you can show regarding this type of cost. And the algorithm would be like the trivial algorithm that everybody would use on this problem, but actually it's quite well known on quadratic programming, is to do this relation over and over. So what you do is you do this linear, so you have some guess for the pi coupling. You do the linearization and you solve an optimal transport problem and you solve it over and over and you cross the finger and hope you converge to some nice solution, which in practice often happens. So it's not so clear why, but I would go quickly on this. There is also another work by Mondino and De Ponti that does a very similar thing. So there are a few teams that work on the same idea of trying to relax relax Gromov-Wasserstein to the unbalanced case. And the only trick, the thing that you need to do if you want to have some nice property is you need to relax it, but don't use the usual, I would say the usual relative entropy. You need to do the relative entropy squared, meaning you need to use the relative entropy between the tensorized version of the marginal and themselves. And it is, I mean, the intuitive reason why is to have the same homogeneity somehow as the functional you are minimizing. And you can show that this is not defining a distance, unfortunately. On contrary to the optimal transport case, it's not a distance, but you can show that it's related, or actually upper bounded, by a true distance, which is a conic distance in the sense of Mielke and Savary and Liro. So I will not say more about this. If you're interested, you can read the paper. And you can use it in practice to do, as I said before, registration between multi-omics data. Some open problem to conclude, I would say on the theory or on the gradient flow side of the story, the obvious open problem is to extend classical result or the result of Lénaïc to a deeper network, and it turned out to be super complicated. It's not obvious how to do it. What people would do numerically or in practice in neural network to go really deeper is not to just stack more layers, is to do what they call a residual network. So to typically have a small network and you iterate this network over and over. But what you do is a skip connection. So you add the input as here at the end. And this allows you to have a much more stable training. And it's really connected to solving ODEs. So one question is like typically related to control of ODEs. There is also a class of architectures that does things more complicated. That's called transformers architecture. If you're interested with this, you can come to me. But these are architectures that don't only operate over a single point. They typically take the data, break it into a lot of points. Like if it's an image, it's going to be a lot of patches. If it's a language model, it's going to be words that are embedded. And then you would evolve using your network this group of points together during the layers. And this is very similar to Wasserstein gradient flow. So I think there is also a lot to learn between the interface between gradient flows and neural architecture. Maybe Marco would say a few words about this. And regarding Gromov-Wasserstein, I've already said this, but the key open problem is existence of Monge map, and maybe also study what's happened when you introduce entropy. Thanks a lot for your attention, and I'm stopping here.
Thank you, Gabriel, for a nice presentation. Are there any questions, comments? There's one back there.
Thanks. So for the ATAC-seq and the RNA-seq data, usually you actually get both for a single cell now. So does it validate well using Gromov-Wasserstein for registration of those two data sets?
So on small data sets, they could do paired data for which they know actually the exact matching. So what they would do is typically, yes, evaluate the performance of different algorithms on small data sets. But for large data sets that would go to 100 and 1,000, they don't have paired data. So they rely on the analysis they do on small data sets to say that, I mean, one method that works well on small data set is validated, and then they apply it to much larger data sets.
Thanks.
Or at least it's my understanding of their pipeline.
Maybe I'll ask one quick question. You mentioned sparsity convolution at some point that can be solved with this type of approach. Has anybody compared this with more traditional approaches based on, say, Tikhonov regularization combined with some?
Yeah, so it's a very good question. So in practice, I've simplified a lot. So in practice, we would do what you say, so adding a regularity to do like a Tikhonov stabilization. And this is also explained in the work of Lénaïc. So I've just, for simplicity, I've removed the regularization. You could really see this as just another solver. It's not a new type of functionals, but it's another solver where you would optimize both on the grid position and on the particle position. So classical method that would solve Tikhonov, like lasso or reach, they would fix the particle and they would just do unbalanced. So in some sense, it's quite fun because what people do for a lot of time was just purely unbalanced, where they don't move the particle. And here we just move the grid at the same time as we move the particle, which is not new. There are other people that do similarly, but it's like interpreting what people would do in the language of optimal transport.
Okay, thank you. Let's thank the speaker once again.
This was mentioned as well. The Synchron primal problem that I just presented with this entropic regularization is a bit simpler, in fact, when you look at the dual formulation corresponding to this primal. And the dual formulation, why is it a bit simpler? Because it has no constraints. It's a very simple to write, maximization problem with this linear term in alpha and beta, and then this composite term here, which involves this double summation. And if you look at the first order conditions for this energy with respect to alpha, and you cancel them so that the gradient with respect to alpha is 0, you get this update, which is the lock space if you want synchron. And if you cancel the gradient with respect to the second variable, beta here, you get this update. And each of them, of course, corresponds to this other thing. So it's usually a lot more convenient to work with this dual formulation. So I wanted to say a few words about differentiability. So whenever you will use optimal transport, let's say in a pipeline, there's, in my experience, two different ways you might want to, two different things you might want to differentiate, and they are completely different. One might be just simply the objective, so what we would call the Wasserstein distance. You want to differentiate it. Typically, Gabriel was talking about gradient flow of the distance. So you change the positions of the particles, and in that case, it's quite simple to see that you can use the envelope theorem essentially. So here, I'm not even using regularization. This is a bit the extreme case. Imagine I'm going to use a perturbation of the inputs x, and I'm going to use the primal for this. Well, you can see that if you perturb a little bit, your inputs x, and you get a different cost matrix. Essentially, the cost of optimal transport at x plus delta x with the matrix x plus delta x as the cost matrix, the only thing that is actually changing or moving here, literally, is just simply the cost matrix itself. So in a way, if you want to compute the gradient of your Wasserstein distance with respect to anything, so here I just did this animation with x. If it was with the weights a, I would have used the dual formulation. Then it's as trivial as simply freezing the solutions, either in the primal or in the dual, and computing the derivative, of whatever you're interested in. So this is usually called the envelope theorem or Danskin's theorem. What I think is interesting for the community and has been used in a few applications already is not too much to think about the differentiability of the cost, or basically the objective, but more about the optimal solution. And so here, this is again a picture which is meant to be a bit caricatural. Here I have changed the inputs. My linear program is still returning the same P star. And so in a way here, we are in a situation where the Jacobian of P star with respect to the input is actually 0. Nothing has changed. And if you're familiar with neural network optimization, but even if you're not, the key thing in this setup, when you're training those very large architecture, is essentially that the gradient flows through parameters. So here you're basically telling me, if you're using optimal transport allocation here, that P star didn't care. It's like the change in x basically is not going to impact the P star locally infinitesimally. Of course, what will happen in practice is that you will jump to a different corner. So here again, the solution, and this is yet another reason why you should definitely consider entropic regularization for optimal transport, is that the solution P gamma intuitively is going to move in a lot more smoother way with respect to the inputs. So if I had to make a picture, you can see that P gamma would be differentiated continuously with respect to whatever parameter you provide. So this is the intuition. In practice, how you can get this. There's essentially two ways to do this. One is very familiar with anyone studying this type of algorithms, and it's simply unrolling the iteration. So you just see the synchron algorithm that we've seen so many times as something you run for 100 iterations. You stop when you're happy, when you feel you have converged, and then you just unroll or just differentiate the sequence of steps which are all very elementary. So this works. However, I put a warning sign here because there's two issues with this approach. The first issue is memory consumption, because you need to store the iterations. There are some workarounds, but there will always be a pain, problem there. And the other, I would say, issue with unrolling iterations is that this is really dependent on the computational graph. And so you can somewhat backtrack and go back the synchron iterations if what you've done at every step was actually quite naive. And this is, by quite naive, I just mean the regular synchron iterations. Recently, people are considering more, let's say, smarter choices for the synchron iterations, which would involve momentum, for instance, or even Anderson acceleration. And those steps are not differentiable. And so they somewhat prevent, they make this not a very flexible framework. So what is the other approach that you could use, of course, is to see this more as a mathematician. We are essentially given a optimization problem. What we want to do is, given the inputs, the measures, the cost, the regularization, I have this energy, and I know that the solution is something that cancels, those two gradients. So if I were to define this multi-valued map here, H, which to all of this people here outputs the gradient with respect to alpha of the energy evaluated there, then what I want is that this H map is equal to 0, basically, when I'm evaluating it on the alpha star, beta star that corresponds to these inputs. So what we do is the following. We just say we have a map that takes the inputs and outputs the transport, here represented as the dual variables. I am going to define this root equation. The root equation here is 0 when I inject the inputs and the solution corresponding to the inputs. And what I want to do is differentiate those outputs here with respect to any of the inputs. So we just use the implicit function theorem. So the implicit function theorem will be telling you that the Jacobian of the outputs here, so the transport, the dual variables, is going to be given by solving this linear system that involves the Jacobian of this root equation evaluated alternatively on those two variables and on whatever here you want to differentiate against. So just a technical aspect. In practice, we will rarely use or instantiate this Jacobian. What we want to do is, why do we want to do this? Why do we want to do implicit function differentiation in this case? It's because we are going to use optimal transport, in some step of your, let's say, learning pipeline. You do some kind of, either sorting, or you just do some assignment to clusters, things like that require some optimal transport solution. And in the end, you want to minimize some loss that will involve those things. So when you do this, you're never really asking for the Jacobian of the optimal transport solution with respect to inputs. The only thing you need is essentially to differentiate, compute the gradient of a loss that depends on the optimal transport. So optimal transport, again, is just an intermediate step. And in that case, what we know is that if you use reverse mode differentiation, what matters is not so much the access to this Jacobian. The only thing that matters is being able to apply the transpose of that Jacobian to a vector, which is essentially going to be itself backpropagated through other steps. So in other words, if really what I want is this, if I just start from the implicit function theorem, what I'm actually aiming at is solving this linear system. And although this might seem a bit complicated, it's actually very simple to instantiate this automatically using Jack's primitives. So here, Jack's primitive for this would be VGP, so vector Jacobian product. And this is done automatically. This instantiates a function which is able to apply to a vector, this VGP. And you can also instantiate a sparse linear system solver that is going to do this computation as well. So in other words, this is all implemented in Not. And so if you wanted, for instance, to compute, let's say, the Hessian of the synchron divergence that Gabriel introduced a bit earlier with respect, let's say, the weights or with the locations, it's just as typing, dot Hessian, Jack's dot Hessian of synchron, and then getting directly those estimates. So a quick word about the synchron algorithm, because it's been around for a while, but there's one minor aspect that I think has been a bit overlooked, which is that you need to initialize the synchron algorithm. And typically you initialize either of alpha or beta. So if you start with this iteration, you will initialize beta, and then you're given alpha, and so you can re-inject it. And so if you look at implementations, most of these implementations will rely on initializing the synchron algorithm with zeros, which is not so bad, because in the end, synchron being a convex problem is going to converge whatever you feed it, as an initializer. And this is also a point that I raised a bit earlier. One of the reasons why people don't want or didn't want to put too much emphasis on initializing with a clever trick is that this could break the differentiability of the unrolling of approaches if you were using unrolling. However, what I just showed is that if you use the implicit function theorem, you're only using the quality of the solution. You're not really using anything of how you got basically to the solution. And so the question we asked with James is, can we do something a bit more clever? And there's a few cases which actually for which you can get significant gains. One is maybe a bit counterintuitive, and it's the idea of solving the 1D optimal transport problem with regularization. It's counterintuitive because you could think sorting, gives you the solution in 1D. So why would you use to quadratic algorithms such as Sinkhorn? The reason is that if you use regularized optimal transport on 1D problems, you can get quantities that look like soft rankings or soft sorting operators. And we've been using this in other applications. And so trust me, there is a point. I mean, there is a reason why you might want to run Sinkhorn on a 1D problem, even though the regular optimal transport is not in closed form. And so in that case, well, it's maybe a bit stupid, but actually using the dual variables that you get from the 1D problem that is not regularized, so it's one of those completely head over heels, examples where optimal transport, the naive one, gets you solutions for very cheap. You feed them into Sinkhorn. Well, of course, then you converge much, much faster. So let me just try to explain a bit those plots. We're sampling randomly arrays of 1D arrays of, let's say, 2 power 10 points. And I am comparing the number of iterations Sinkhorn requires to go to convergence. And here what we have compared is zeros. This is the zero initialization. And to be actually fair, we've used all of the tricks that people use around to improve Sinkhorn. So here I have at the default, this is just regular Sinkhorn, Anderson acceleration, momentum with a fixed size. This is an adaptive momentum rule that Max von Renesse and his team have proposed that work very well in practice. Epsilon decaying. There's lots of things you can try to modify to get a faster Sinkhorn. But of course, here in this case, starting from the 1D solution, actually, non-regularized one works very well. And here we try to do the same thing. The other trick, which is also a bit surprisingly naive, but which works very well, is just to rely on Gaussians. So for Gaussians, let's say I have 2 data sets. Of course, I would take a Gaussian approximation. If I do a Gaussian approximation, I have the Monge map in closed form. I also get the dual potential in closed form. And so what we are just proposing is as naive as just simply pre-computing this and just fitting it, to your vector alpha of dual variables to start. And so what we've proposed a few other extensions using, for instance, using GMMs. And what we observe is that, so this is a task, it's a bit of a pretext task of comparing point clouds in high dimensions. Those are word embeddings, word embedding point clouds, so text. And what we see is that using this Gaussian, approximation in terms of number of iterations saves you a lot on the regular zero dual variables. And if you start factoring it, pre-processing time, well, the picture is a bit more complicated because in some cases you might have to in the GMM case that I didn't really here explain, you might have to do some pre-processing of computing the GMMs, estimating GMMs on your point clouds first, and then use those GMM approximations. And then here subsample is actually the simple strategy of taking a subset of points in your point clouds, running Sinkhorn on this, and using this Sinkhorn extrapolation on all the other points to initialize Sinkhorn. So let me now briefly go towards this low rank approach and why I think it's quite exciting numerically. So the idea of the low rank approach is actually very intuitive. It's the following. We are always looking for transportation tables in this polytope, which are of size n times m. We know that those matrices, if we are dealing with a not regularized case, they will be full rank, of course, because essentially, even if you think about the 1D case, you have this it's supported on the Monge map. So at the limit, of course, any optimal transport will be, except in very degenerate cases, full rank. But a bit using the same principle that the entropic regularization, we want to actually move away from Monge, move a bit more away from Monge than what Kantorovich does. we propose to directly say, well, let's directly optimize this problem here using a rank constraint. And so I remember that with Gabriel in 2016, we were thinking about using a trace norm type of regularizers and things like that. And then maybe to 2020, Gabriel had the idea of, well, why don't we just do like everyone, which is like to directly impose this low rank constraint directly on the matrices. And then we realized that this idea had been also considered by one of the team of Philippe in a slightly more explicit form, where they were actually doing a low rank in the, let's say, 2 Wasserstein case that was transiting through some intermediate points. But let me just try to do what we did, which is a bit more like a linear algebra perspective. It's just to say, if you take a matrix Q, which has row sums A and column sums G, where G is any vector in the simplex, and you take any matrix R, which is itself a coupling with B and G, the same G, and you form this product of 3 matrices where you start with Q, take this renormalization 1 over G, and again multiply by R transpose here, you get something which is a valid coupling. And so the intuition is, therefore, can we just think about optimizing this linear problem, the regular problem, using this parameterization as a product of 3 matrices. So of course, what we lose here is convexity. This is the typical setting where we are going to have issues with careful initializations, clever initializations, and so we've been putting some effort into this. But what we gain is that if we just think about doing Dijkstra's algorithm, or just simply here, for the sake of simplicity, alternate optimization, what we have is essentially 3 problems where we can cycle through, optimizing each of those components. And if you think about it, each of those problems here is, of course, this is if R is the size of this, bottleneck here in the middle, this is a problem of size NR. And here you would need to compute a cost matrix of size NR, but you will need to solve basically 2 optimal transport problems here. And then this is a much simpler problem on just a vector. And so here, to be honest, we re-inject a bit of entropic regularization but with a decrease of gamma that goes to 0. And just a small comment, if we're able, of course this is always the case for the Euclidean, square Euclidean case, to factorize this cost matrix as itself a product of low rank factors. So if you are, let's say, in dimension D, you will always be able to factorize this as the product of D+2 of rank D+2 matrices. Then those evaluations here in the middle become linear in the sense that they are number of points times R times the dimension of your factorization here. So this was already quite a cool thing. So let me just try to give you a feeling of what you get. It's a different type of regularization. Here, if I impose the rank of this coupling to be equals to 3, this is what I get. If I have a big regularization in entropy, I get something very blurry. And so you see that they will both converge in the end towards this maximal rank, minimal entropy solution. But what we're saying is this is actually more efficient, in practice. Let me just try to explain also why this is useful in the Gromov-Wasserstein case, and I think this is the application that we were targeting from the start. Remember, in the Gromov-Wasserstein case, we have this energy which is quadratic in the coupling matrix, and what we do is this linearization that we keep on doing like this. Just in a particular case where we are using this square to score the deviation between that matching, then essentially that gradient is a product of the 2 cost matrices with P here in the middle. And so here is why it's a bit, of course, I'm dropping the formula here at you. It's a bit heavy, but what I want to say is that if you replace those P's here and the PTs here by a low rank formulation all the time, so you're always staying low rank, then you can see that I am essentially this is basically my C1, this is my P, this is my C2. Everyone is low rank, even the cost matrices are low rank. And so this stays like a low rank resolution. And so here we have a Gromov-Wasserstein solver that works quite well, and that scales up to hundreds of thousands of points. And so one of the applications we're seeing now, we're going to release this toolbox called Moscot. So this is Fabian Theis' lab in Munich, which is called multi-omics single cell optimal transport, and it builds on OT, and OT already implements all of this. And so it's already, without even you telling, OT, that this, let's say, low rank, it's going to compute a low rank approximation of your cost matrices so that you can switch to this better regime. This, of course, implies a lot of engineering issues with respect to how to set the right regularization parameters and the scaling, etc. But I think for now we're dealing with it quite well. So let me just switch very quickly to the other more neural. Yes.
Can I ask a question?
Yes, please.
Do you have to determine R in advance, or can
Yes.
you do it adaptively?
No, we for now we just determine it in advance. It's a bit like a K-means. I just rules of thumb. Just let's say just like K-means basically. So you could it will essentially, it's a trade-off also that is computational clearly, and so we try to set an R that is big enough so that it captures things, but small enough so that computations don't blow up.
Seems that you would need to know something about the decay of the singular values to make a good determination of R.
Yeah, but the problem is that the real optimal transport, it's not going to decay. The singular values of P are always going to be, of course, except if you start using weights that are maybe smaller, some of them. But again, I think the gist here is to say that we're not losing by using a small R. This is more like really we want it, even statistically it's better. And so Meyer and I, but it's mostly Meyer, has written a paper that is going to be published at NeurIPS that also makes a case statistically for this low rank approach. It's a bit like the question of setting gamma for epsilon for entropy. So neural networks. Okay, this is the Monge problem, this is Cantor-Ridge problem. We know that in the case where we have some knowledge about the cost, we can say a lot of interesting things. So if the cost is the one cost, the distance, then we have the Lipschitz formulation, and we know that otherwise it's as easy as solving the problem with convex functions. So what is a good parameterization of convex function that you could come up with that uses this neural network approach? So if there's one slide maybe that I'd like to stress a bit is this one, which explains this construction. And this was proposed completely independently of optimal transport in 2017. And this is something people call input convex neural networks. So let me try to explain why this encodes an interesting family of convex functions. So the formula is as follows. We have a vector. As usual with neural networks, we just don't care too much about the sizes of the vectors. This is something you can set. And we update it by step after step. It's like a recurrent process. We just say we take the formula vector, we multiply by a matrix. We take X, we multiply it by a matrix. So somewhat the sizes should be, of course, in agreement. And then we apply a nonlinearity. And at the end, you make sure that those matrices are actually just collapsed, just row vectors, so that you get just a value. So let me just try to do this graphically. X, remember, here is our input. Z0 is just initialization of this vector. It could be 0. So X, you multiply it by WX, and you add some B0. And Z, you multiply it by a matrix. Each of the entries of that vector, you let them go through a nonlinearity. And the nonlinearity here I'm plotting is, and this will be important, increasing and convex. So you do this again, you get this Z1, and you do this again and again. So it's a bit like a recurrent neural network, where you have a state here, and you reinject, or more like a residual network, sorry, and you're reinjecting all the time this X here, okay? And so here's the way I think you should interpret a bit this construction. First, the end result, so at the last layer, you're not multiplying by a matrix, but just by a vector. The end thing, which is just a number, is going to be convex with respect to X if all of those matrices here are non-negative, have non-negative entries, and the sigma i's are increasing convex. So here's what's my intuition about this. Essentially, every time you multiply X by a linear function, you have a convex entry. So every time I'm going to multiply X by this matrix, I'm going to have a vector, which is just an affine quantity of X, which is by design, of course, convex. And I am going to add, so Z0 at the beginning might be zeros, but actually you can do something a bit more clever. But then if you think about this vector of entries, since at the beginning it's just affine, if you apply an increasing convex function to each of the entries, you still get something that is convex. And so if you want, the vector z is a bit like a bank of convex functions of the input x, and you're at each iteration you're refining it by adding a bit of linearity and then again convexification. And so in the end you get a quantity that is convex. And so the way people train this in practice is they will use a surrogate function g, which they penalize to look like the Legendre transform of f on the samples that you have. Hence here, this term that pops up. So you will basically try to find the convex function f, and at the same time optimize something that should look a bit like the Legendre transform of f, and then use the simple dual objective of the dual conservation problem. And so if this is implemented in knots, and let me try to explain how we use this in two settings. So Gabriel mentioned this idea of looking at biology problems as essentially cells that move with time, and the issues that are attached to this, which is that you can monitor cells, but every time you actually measure them, you kill them. So essentially what you're given when you're looking at those cells over time and you're doing single cell genomics is just a sequence of point clouds which are not registered. You don't know who is who, but statistically you have enough samples to believe that, well, if that cell had lived, if I hadn't killed it to measure it, it would be somewhere here. And so the challenge, the challenge is to use optimal transfer here. So this is, again, as Gabriel said, work by Schibinger et al. That includes Philippe as a co-author. And what we try to do is look at this and basically model this as a time evolution, maybe just simply as a gradient flow to start. And so people propose this. This is a paper by Hashimoto. They said, well, if we believe the particles are moving according to some gradient flow, and we want to estimate this potential E, what we could do is propose this dynamic model. We have the data. We start from the data. So this is the data that you observe. And this is our model. And the model is just simply saying, at each iteration, the particles are moved according to some potential, the gradient of some potential that I'm going to parameterize as a neural network. And I am going to fit this essentially by trying to minimize the distance, the Wasserstein distance, using Sinkhorn because it's convenient, between my data and essentially my prediction. Okay, so it's a simple model where you're just making this assumption that everything is moving according to this gradient, and you minimize with the Wasserstein loss. There is, however, a bit of an issue here. If you do this in a straightforward manner, that I'd like just simply to highlight by just zooming on one particular step. Imagine my measure at rho t, that is before I compare it with the data at t+1, is this thing. Imagine this is my data. So essentially what I want is that in Wasserstein sense, the gradient of this potential here, E psi, is pointing in Wasserstein sense towards my blue measure here at the data t+1. One of the issues that we have with this, I'm sorry, this should be an E and not a G. One of the issues that we have with this is that in this model, of course, there's not going to be a difference between this displacement here and this displacement here. And so somewhat what we want to do using JKO here in this setup is we're going to impose that the dynamical model is not going to be just simply a gradient for particles, but it's going to be a JKO step. And then we are doing an inverse JKO problem because what we want to do essentially is estimate the energy whose JKO trajectory that we are constructing as a model. We want this trajectory here to fit the data. So the data is going to be basically taken into consideration with respect to this fitting loss. And this rho t x plus xi t+1 is essentially the solution of the JKO step. So this is there's a few complexities here that are piling up. So how do we parameterize this? Well, this is a nice reparameterization that was proposed by Jean-David and his team in 2016, is essentially to say, if we're solving the JKO step by minimizing with respect to the measure rho, we might as well reparameterize those measures rho by being just simply the gradient of a convex function applied to the previous measure rho t, and then try to basically find a good convex function that does the job. That is both decreasing your energy and at the same time having a low Wasserstein distance. Of course, if you're following the gradient of convex function here, we have the Wasserstein distance in closed form. So this is actually a fairly simple problem to carry out if you can parameterize the space of convex function, and this is what we do with ICNNs, of course. And so to sum up, what we do is, first, we solve an input convex neural network to solve this problem. Once we have found the theta star, this best convex function, we re-inject it to model the next step, and then we just want to make the Wasserstein distance smaller. And so this is a bi-level optimization problem. In the upper optimization, we're trying to optimize with respect to parameters, and the lower level optimization, this is the ICNN. If you want, it's a commute variable. We're trying to improve on this. So I think I have 2 minutes, 3 minutes. No, it's done. Okay, I would just want to highlight. This is 3 slides. This is a New Rips paper that we just published, and I think it's very exciting. Optimal transport, of course, is used in practice, and people are going to use this in genomics. And what people have, as data in genomics is typically a context. They have a measure, okay? They will have a measure of cells, another measure of cells. This could be, for instance, after some treatment. And ideally, what they want is to say, oh, this treatment is well modeled by this Monge map. And this is basically what this looks like, okay? So I'm starting here, I'm getting there. And for each treatment, you would get one Monge map. One of the problems that we have is that most of the time, there is some additional information which is given to you, which you need to take into account. And that information might be quite high dimensional. So typically it could be some of the cells, are gray cells and some of them are blue. So maybe you want to estimate 2 different optimal transports. And so what we propose is, instead of actually estimating an optimal transport for each different context, is to do some kind of joint conditional optimal transport estimation that will be able to recover, if you give it as a side information, a context, a different transport. So essentially what we're trying to do is to define parameterized families of Monge maps. And let me just try to give you one example where this is very exciting. Imagine I am able to estimate the Monge map that explains what happens to the cells when I give them a first treatment. And I am able to estimate a Monge map that explains what happens to the cells when I give them a second treatment. Can I somewhat try to extrapolate a Monge map that will explain what happens to the cells when I give them both treatments? And so if you're using optimal transport, in a way, it's a bit as saying that we want to estimate a family of Monge maps using the data sets that is parameterized by some context variable. And just to be a bit brief, it's possible to do this contextualization, if you want, at the level of those input convex neural networks by using something which is called a PICNN, a partially input convex neural network. So we're going to do a simultaneous, so rather than having 2 measures of estimate optimal transport, what we do is simultaneous estimation of multiple optimal transport maps using a family of Monge maps that is basically interrelated. So I'm sorry, this was a bit fast. So this provides some exciting results on trying to extrapolate what happens, let's say, to combinations of perturbations, so treatments, or let's say knocking off some genes. So that I will just conclude here. Thank you very much for your time.
I propose that anyone who has questions for Marco can ask them during the coffee break. We'll reconvene here at 11. Thank you. Welcome back, everyone, for this second half of the morning session. It's my pleasure to introduce Lénaïc Chizat from EPFL, and this is the title of his talk.
Thank you for the introduction. I'm very glad to be here, and thank you for the invitation. So unfortunately, I will only attend this conference today because I have several classes to teach this week. I would have preferred to stay here the whole week because all the titles are amazing, but unfortunately, if you want to discuss with me, and it will be only today, I will leave tomorrow morning. So we'll talk about Wasserstein gradient flows in relation to entropic optimal transport. So in general, what I want to discuss is a set of tools that allow to use particle-based optimization methods in relation to problems that involve entropic optimal transport. So of course, we will not just consider the entropic optimal transport objective functional, but some more complicated problems that involve this. The main guideline, the main guiding example I will talk about is the one of regularized Wasserstein barycenters, how to compute such barycenters. And in the end of my talk, I will talk about the very interesting problem of trajectory inference that was already mentioned by Marco and Gabriel this morning. All right, so this talk will be organized in those 4 parts. So first, I will describe this problem of entropic Wasserstein barycenters that I want to solve and to find numerical methods to minimize. Then we will see that these optimization methods will involve some partial differential equations, and we need to understand whether they exist and are well posed and are unique. Then I will discuss the long-term convergence of such kind of partial differential equations. And finally, I will briefly go over the problem of trajectory inference, where entropic optimal transport will also play a role. So let me introduce this problem of entropic Wasserstein barycenters. So for that, I need to introduce a few notations. In all my talk, I will consider a compact convex subset of RD, which will be the domain. The compactness will be important, in fact, for some of the stability results I will present. Dx is the Lebesgue measure, and I consider 2 probability measures, mu and nu. So everything is balanced in my talk. There's no unbalancedness. So only probability measures. I will denote by H the relative entropy. So this is what was sometimes denoted by KL, between mu and nu. And H of nu is the relative entropy between, with respect to the Lebesgue measure, which is the negentropy, differential entropy. And I will call it H of mu. So with these quantities, we can define the entropic optimal transport, which is the entropy regularization of optimal transport. We choose a smooth cost function, C, from X to R. Pi of mu nu will be the set of transport plans. Lambda is the regularization level. Okay. And I will define by T lambda of mu nu the value of the entropic optimal transport problem, which is the problem of optimal transport, where I add inside the optimization a relative entropy of the optimal transport plan with respect to the product measure mu times nu. So the choice of the product measure, of the reference measure here, it matters a lot for the kind of results I want to discuss. So I just wanted to state a few remarks before moving on, that if instead of regularizing with respect to the product measure, we had regularized with respect to, let's say, the volume measure, the reference measure Lebesgue, then we would get a problem which is only well defined when the 2 marginals mu and nu have finite entropy, but you have a simple relationship between the 2 problems. So if you just add some entropies, lambda times the entropies of mu and nu to this quantity, this is this problem, which is often called the Schrödinger problem when we regularize with respect to the Lebesgue measure. And they have slightly different properties, which also I'd like to stress before moving on, that this minimum will give a value which is jointly convex in the 2 marginals mu and nu. So this can be seen by looking at the dual. You can see that the dual is a supremum of linear forms. While the T lambda is only separately convex in mu and nu. So we see that adding a bit of entropy to this value gives us additional convexity. Okay, when we add the entropy of mu and of nu times lambda to T lambda, we get something which is convex in both marginals jointly. These are the technical preliminaries. And now the problem, which will be our motivation to study some Wasserstein gradient flows, is the following problem of entropic Wasserstein barycenters. So we consider K probability measures, a priori with no regularity on X, K weights, which will sum to 1, and we want to solve this modification of the Wasserstein barycenter problem. So here, it's a bit subtle because this is a formulation which I don't think I've ever seen it in the literature. Sometimes when we regularize the Wasserstein barycenter problem, we just replace T0, so T0 would be the unregularized optimal transport cost with some regularized version. But here we both regularize here, and then we also add the entropy of the barycenter as an additional, I mean, it looks like an additional regularization, but in fact, it has the opposite effect. Okay, so here, sometimes there are formulations of Wasserstein barycenters which are regularized by just adding the entropy or just regularizing the optimal transport problem. Here I'm doing both with the specific factor lambda over 2. Why is this formulation interesting? So I will briefly go over the two first points, which are not the topic of today's talk, and then I will discuss at length the third one. So the first one is that when we add the entropy, we have a better approximation of the unregularized Wasserstein barycenter objective. In fact, we can see that when when the new eyes have, let's say, finite Fisher information and some other, like we also need to assume some smoothness of optimal transport plans, then this quantity is a lambda 2 approximation of the unregularized quantity, so with T0. So you see that lambda over 2 times the entropy is exactly the right term to correct the first order error with respect to the unregularized objective. A second nice aspect is that this formulation gives barycenters which are stable. They can be estimated quite efficiently. So these two results, they will be in the preprint, which is not yet online. And then today, I will talk about the optimization for this problem. So what we want is to have a method that can compute this kind of barycenters without grid. Just think of dimensions which are too high to grid the space. We want just particle-based optimization methods with some theoretical guarantees to find the actual barycenter. And this is what I want to discuss today. And the kind of algorithm we will consider are the following. So I call G the first component, the first term in this optimization problem. So we have our objective function is G plus lambda over 2 times H. The technique is as follows. We discretize the measure in particles. X parameterizes the position of my atoms. Here, there is no unbalancedness. So let's say all the direct masses have the mass 1 over m. And I initialize them randomly by sampling independently from some mu0 probability distribution. And then I run gradient descent just on the term G. So here, of course, if I just do that, I will only minimize, or maybe try to minimize, there's no guarantee that I will not be stuck in local minima, the first term, G. But what we do more specifically is a noisy gradient descent. And so the noise should be able to take into account the other entropy term. Okay? So what we want to discuss is when m goes to plus infinity, we'll have some mean field optimization method. We want to understand whether it's well posed, like this unique solutions, and whether it converges to the global minimizer, so whether it's actually able to compute the barycenter of this problem. So let me show you some illustration. So here, this is, we have a mixture of the blue, the orange, and the green distribution. So you see the blue has two modes, and the green and orange are just Gaussian, like sample points, sampled from a Gaussian. And we want to compute the barycenter of this tree distribution. So the algorithm will follow the black particles. And what we would like to recover is this, essentially this shape, two clouds like that, which are the barycenter, the Wasserstein barycenter. So here, yeah, I approximated with another algorithm the two barycenter that we would like to obtain. If I only do gradient descent on the position of the particles, I get that. So this is a well-known bias due to the entropic regularization that makes the distribution collapse. And here, if I do noisy gradient descent, I get this solution, which is much closer to the actual solution. So the additional entropic regularization, in fact, allows to debias the objective. There are other ways to debias the entropic barycenters, for instance, by using the Sinkhorn divergence. There is a paper by Cuturi and co-authors on that. But here, I focus on this technique for debiasing because, as I will show, it allows to also have global guarantees on the solution of the problem, of the dynamic. Okay, so that was a first illustration for the debiasing effect. Now I will show another illustration to observe that it tends to not get stuck in local minima. So here, this is an example where I have a measure mu in blue and a second measure in orange. So both measures are two direct masses. And I want to compute their barycenter. So it's an example I've learned from Hugo Lavenant, maybe it's a classical one. If I start from the black points, so here this is a stationary point of the objective function G. Let's say I do the gradient flow on the barycenter objective and I want to compute the barycenter of the blue and the orange measures. This is a stable stationary point. However, this is not the barycenter. The true barycenter, in fact, amounts to putting one particle in the mid-line, like in the middle between these 2 points, and another particle in the middle between these 2 points. That would be the true Wasserstein barycenter. So if I do not add noise, I would, like any numerical method, would get stuck here. But now if I add noise and I have a particle method, we see that somehow it escapes this stationary point. So of course we have a little bit of bias, so we do not converge to direct masses, but overall it escapes the stationary point and get closer to the actual solution we are looking for. Okay, so some comments on this algorithm. So each iteration, as I will explain a bit more, it involves solving one entropic optimal transport problem. This can be done via Sinkorn's algorithm, and the general complexity is overall linear in everything we would like. K here is the number of barycenters, D the dimension, N the number of particles in each of the marginals, M the number of particles that we optimize over, and lambda epsilon here are the accuracy and the regularization level. So it's quite like it's a good, interesting computational situation. But this is just to compute one iteration of the gradient descent. And now the question is, of course, will we converge? How fast? Or this kind of thing. So what I will discuss is in the mean field limit. So when M, the number of particles that you see evolving, go to plus infinity, we have a well-posed dynamics. Does it converge to the global minimum? And at what speed? So as I said, more generally, this is, you can think of it as a showcase example of how entropic optimal transport interacts with particle-based optimization. And in the end of the talk, I will present different applications to, for instance, trajectory inference. So let me first discuss the well-posedness of the mean field limit. So in this talk, I will not discuss how to pass to the mean field limit and quantitative estimates of the error that we make by discretizing in terms of particles. These are very interesting questions, but there are still some work to do on that aspect. But I will directly consider the mean field system, so with M equal to plus infinity. So to clarify a bit, I will just look at one marginal. So we just want to minimize the entropic optimal transport distance between, like, towards the target measure. In that setting, the first variation of my objective function G is given by phi mu, which is the first so-called Schrödinger potential. So Schrödinger potentials are the solution of the Schrödinger system, which is exactly the equivalence of the Cantor-Rich potentials of optimal transport, except that now we have regularization. And as we have seen in previous talks, it's just a smooth C transform that we have on both sides. And phi and psi need to satisfy this equation everywhere on our domain. So that's the equations that characterize the first variation, that is the gradient of our objective function G. And in terms of this phi mu, the dynamics that we get in the limit M goes to plus infinity, and here these are given N-Earth regularity, which I will discuss right after. This is quite standard to pass to the limit, and we have a solution of the following partial differential equation. You are given an initialization mu0, and you follow this drift diffusion equation, where the drift is given by the gradient of the first Schrödinger potential, and the diffusion has this factor lambda over 2, which was our entropic regularization. And this is the effect of the noise. So formally, this is the Wasserstein gradient flow of the functional G plus lambda 2 over H, the thing we want to minimize, which I call F. And for this, we know that, for instance, if G is displacement convex, for instance, this is well posed. This is not our case. G is not displacement convex in general. It's not even convex along general geodesics. However, it has some sort of smoothness, which is sufficient to prove well-posedness of this system. The kind of smoothness that we want to prove is essentially, it corresponds to G being lambda geodesically convex for some lambda which is negative, and minus G also being lambda geodesically convex or some lambda negative. So I use this word displacement smooth because smoothness in optimization is really saying that we have Lipschitz gradients, and this is what we will show in this case. So we'll show that G has Lipschitz gradients as seen in Wasserstein space. And when we show that, then we have no problem to conclude that this dynamics is well posed for any initialization, no regularization, no particular condition on density and so on, any mu 0. So to understand the regularity of G, we need to understand the stability of entropic optimal transport. So that will be the first result I wanted to show. We often hear that optimal transport is smooth and regular, but somehow the exact level of smoothness and was not very well known so far. So we have studied this problem with Guillaume and Maxime Laborde, and we have proved the following. So if you have a cost which is smooth enough, then you have the map which to the marginals mu and nu associate the corresponding Schrödinger potentials is a Lipschitz map from the space from the Wasserstein space to the space of CK function. Okay, so you have control over the first K derivatives if the cost is CK plus 1. And here, this particular norm that I've written here is just the usual CK norm, except that we need to quotient by the equivalence relation of functions which are equal up to some exchange of constants, which is the usual trivial subspace of solutions for entropic optimal transport. So we have this stability result for the solution of the Schrödinger problem. And as a corollary, because phi is the first variation of entropic optimal transport, we can deduce that if the cost, for instance, is just C2, then T lambda is displacement smooth. So I recall displacement smooth means T lambda is lambda geodesically convex for some lambda which is potentially negative, so it's not convex, I insist on that. And minus T lambda is also lambda geodesically convex. We have the required regularity to have a well-posedness of the dynamics. And let me give a few words on the proof for this result. Oh, yes, of course, yeah. Yeah, okay, so here, 5 psi are the solution with mu and nu, and 5 psi tilde are the solution with mu tilde and nu tilde. Yeah. Yeah. Yes, so without regularization, the optimality conditions are different, and the regularity theory is very different. Ah, the C, yeah, so the C, I hide it, the dependency. It will typically depend exponentially on the regularization, because we are using some stability of entropic optimal transport, which has this kind of degeneracy. Okay, so, and I insist on the fact that it's crucial to regularize against the product measure to obtain this stability. It would not at all be true if you regularize with something else, with another reference measure. And those results are proved in the multi-marginal case, so you can look at this preprint for more details. Let me give you a proof idea. So let me use these shortcut notations, bold mu for the marginals and bold phi for the Schrödinger potentials. I mean, for some dual variables. So the Schrödinger systems can just be written as a big function which is equal to 0, which is just taking this system and writing it as a function of phi psi and nu. We want this function to be equal to 0. And the idea behind the proof is to consider any transport plan between mu and nu, and then generate some interpolation between mu and nu using this transport plan. It does not necessarily need to be optimal. And then we have a new function which goes from the space of potentials to 0, 1, the time variable, to the space of potentials. And we can apply the implicit function theorem for this function. So there are some details of analysis to check. And in the end, we get the result. And in fact, we have some final regularity results, which I just displayed. I don't need really to comment them, but we have some, like if we know more regularity on the cost C, then we can deduce some smoothness of this map. Here, this is the Schrödinger map, while here, this is smoothness of the entropic optimal transport. So somehow we have quite refined results on this regularity. And here, this is an illustration. I take any pair of measures mu and nu in blue and orange. And in red, this was the evolution of the Schrödinger potential. We see it evolves smoothly, which is what we studied. Okay, so that was the first aspect, the well-posedness of the dynamics. And for this, we needed to understand the stability and the smoothness of entropic optimal transport. So we have, I have presented those results. And now I will study the convergence of these dynamics, that it is well-posed. Does it converge to the actual solution we care about? And for that, I will consider a slightly more general framework, which is sometimes called the framework of mean field Langevin dynamics. So instead of having our function G, which is our Wasserstein objective problem, we will replace G by any function which is convex in the space of measures. Not displacement convex, but convex in the standard sense. So if G was displacement convex, there would be essentially no question. We would know that there is exponential ergodicity. But here we just take a linearly convex function. Also, we assume that it's displacement smooth so that we have well-posedness of the dynamics. And now I'll give a bit more detail on the actual algorithm that I implemented in the previous simulations, which is this, what I call noisy gradient descent, noisy particle gradient descent. So we initialize the points by sampling from some fixed measure mu0. So these are the positions of the direct masses of the particles at initialization. We form the empirical distribution of these particles. So mu xt will be this empirical distribution at time t. And for each iteration, so for time t from equals 0 to plus infinity, we realize the following iteration. So we take the previous position, we go in the direction of minus the gradient of g, gradient in terms of the positions. We add a little bit of noise, which needs to be proportional to the level of entropic regularization. Here, these are IID, like all independent Gaussian variables. And then, since we are on a compact set, we project back on this set to make sure that we do not escape x. So here, this is a projection on x. So this kind of algorithms, when applied to a function which is convex over the space of probability measures, this covers several interesting settings. So there is this problem of regularized Wasserstein barycenters I've mentioned earlier, where it's not difficult to see that it is indeed convex in the variable we want to optimize over, but convex again for the linear structure. There will be a problem of trajectory inference I will mention later. The problem of training shallow neural networks can also be put into this setting, although this is not, I would say, for this particular style of dynamics, is not my favorite application. I prefer the way Gabriel presented it, like with not noisy gradient descent, but unbalanced one. But however, this was the original motivation or networks behind the works that I've introduced this so-called mean field Langevin dynamics. And if you consider G, which is a linear function, just the integral of mu against a fixed function, you recover the Langevin, overdamped Langevin dynamic, which is used for sampling. And okay, there are more examples. Okay, so when we take the limit when m goes to plus infinity for this dynamics, we obtain this equation, which is in the general case, when G is convex, is called the mean field Langevin dynamics. This is the same as before, except that now var phi is the force variation of G, which does not necessarily correspond to the barycenter objective, but can be more general functional to cover these various cases. So this is this force variation. It is sometimes written like that. Okay, at mu. This is a function from x to r, and this can be interpreted as the Wasserstein gradient flow of the function f, our objective function, which is the sum of G plus lambda over 2 times h, the entropy. So that's, now we will study the convergence, long-time behavior of such dynamics in this generalized setting. And the main assumption that I need to present the main convergence results is a uniform log Sobolev inequality. So if you've heard of overdamped Langevin dynamics, you know that if the potential you want to, the density you want to sample from satisfies the log-Sobolev inequality, then you have exponential ergodicity. In fact, the result I will present is a strict generalization of this fact to the nonlinear case, and the main structure that is needed is the convexity of G. So here this is the relative entropy as before. Here this is the relative Fischer information, which is an object, a quantity that naturally appears when we differentiate in time the energy of our problem. And the assumption we will make is that this probability distribution, so the Gibbs distribution associated to the first variation of G at mu. Okay, so this is a bit of an exotic object. Not clear why this could come up in the analysis, but that's what needs to appear. You need to consider this probability measure and need to assume that it satisfies the log-Sobolev inequality for all measures mu, at least in a sublevel of your objective function. So you need this inequality that upper bounds the relative entropy in terms of the Fischer information for all nu tilde any other measure to hold for all measure nu which are of this form. So here I'm being a bit abstract, but I wanted to present it this way. It turns out that in the context, when you're on a compact set, which is the context I'm considering in this talk, you just need that the first variation to have uniformly bounded oscillation. So for instance, for entropic optimal transport, such a constant exists. Unfortunately, it will depend exponentially on -2, minus the diameter over lambda. So you need the regularization level to be somehow of the order of the diameter of your space. But otherwise, this constant will rapidly go to 0. But at least it's satisfied. And once we have such a uniform log-Sobolev property, which is the case for most optimal transport-related applications, as long as we are on a compact set, then we can prove the following result. So it was also proved independently by Nitanda Wu and Suzuki, which is the following. So the mean field Langevin dynamics, the PD which is here, it will converge at an exponential rate. So we need to assume that the initial point has a finite objective value, but then we have exponential convergence in terms of objective function to the global minimizer. We have also the same rates using some Talagrand inequality for Wasserstein distance or relative entropy towards the global minimizer. So the dynamics behave as well as we could expect. It converges to the global minimizer. And this result, when we apply it for the simple case of a linear function, then this is exactly the well-known convergence of overdamped Langevin dynamics to sample from a Gibbs distribution of a potential. So now I will give a few, I want to give a few arguments behind this proof. It can also be generalized to the case of simulated annealing. If you want to minimize not G plus the entropy, but just G, you can do simulated annealing, and with a sufficiently slow decay of the noise, you can also obtain convergence rates, which are very bad, but you can get them. Okay, so let me give an idea behind the proof. I will start with the case of the standard Langevin dynamics, because the proof is an easy generalization of it. So in the case where, so G is a linear function, so the integral of phi against d mu. So this is G, we add H, so I set lambda over 2 equal 1 for simplicity here. Our objective function is this linear term plus the entropy of mu, which, if you rearrange a bit the term, this is just the relative entropy between mu and nu, where nu is the Gibbs distribution associated to phi. So this is the objective function in this case. And the standard proof goes as follows. You differentiate f in time, so f here is just the relative entropy. You get minus the Fischer information against nu, which is this fixed probability measure. Now you use your log-Sobolev inequality. You get this inequality. It turns out that this relative entropy is exactly the suboptimality gap, because f star equals 0 here. And you get a relation between your energy dissipation and the energy. And so you get exponential convergence, where 2 rho will be the rate of your convergence. So now we generalize this argument for the case of mean field Langevin dynamics, which is much more general, because now G is a convex function, but not necessarily a linear function like that. And so the proof works like as follows. So now, instead of having a fixed measure nu, which is the gift distribution, this will be exponential of minus the first variation of g at time t. And we have the two key generalization of the previous fact. The first one is that the energy dissipation is the relative entropy between ut and ut, this function. So that's why I care about this object. It's just because when I differentiate in time the energy, this is the quantity I get. So I can do the first step of my reasoning. Then I have the second step, which is just the assumption of Log-Sobolev inequality, which I've made previously. And then the third step, that's where the convexity of G comes up, which, using the convexity, you can work a bit on the definition of convexity. Notice that the suboptimality is exactly sandwiched between these two relative entropy terms. And so using one of these inequalities, we can close the chain of inequalities and get our Grandval argument. So that's the proof of exponential convergence. Okay. So now, in the last part of my talk, and please don't hesitate to ask questions. Yeah, thanks. Yeah, so that's a good question. So the first proof it can go through for Poincaré inequality, but here I tried to look a bit at it, and it seems I couldn't prove it. So we need to assume something a bit stronger than Poincaré, which is Log-Sobolev inequality. But it seems to me that here the structure is very the structure of the proof really relies on the Wasserstein gradient flow aspect, and Wasserstein gradient flow interpretation of this dynamics only works with the relative entropy, and so I don't think. I mean, my guess is that it's. Yeah. Yeah, but the issue is that I mean, here we don't really have the choice of the metric on the term which is nonlinear G, because we really do the Wasserstein gradient flow. So when you switch to the proof, when you want to study K-square and Poincaré inequality, somehow you're changing the metric structure. You have more, you see the freedom you have in the linear case, but I don't really see that freedom in the more general case. So that would be my intuition that it's not really, not a result I would expect, but maybe. Okay, so in the last part of this talk, I will present another application of this kind of dynamics, so particle methods in relation to entropic optimal transport. And this is a problem that we have already heard about in the previous talks today, which is the problem of trajectory inference. So I will present it a slightly different way. We are still considering our ambient space X, a compact subset of RD, and I will consider the path space omega, the space of continuous functions from 0, 1 to X. And our goal will be to estimate a probability distribution over omega, which will describe the dynamics of some population. Each realization is a path, and we have a full population. So this is the illustration like that. Horizontal axis is the time, and here we have our space. So here, for instance, you have a process that branches. And this can be, for instance, you can think of them as cells that evolved in some RNA expression levels, space. Okay, so this is the kind of object you would like to recover. And the way we observe it is by observing for each sampled path, its position at a certain time ti, but each path is only observed once. So there is this destructive measurement process. And so we cannot expect first to see a certain path several times. So we need some optimal transport tools to reconnect these various marginals. And another point, which is maybe slightly different from the context of Marco's talk, is that we will not assume that we see many samples per time. It could be just one. Okay. So we cannot really use Wasserstein distance between time marginals of the stochastic process because in the setting that I'm considering, we might have only one observation per time, but we have overall many observations, many sample paths. And this is the problem of inference we want to solve. We have this kind of observation. We want to recover the dynamics. And so this is the same motivation that we can have as was presented before, to recover gene expression levels of some sample cells and to understand the full dynamics of the process. And I will consider the estimator that was proposed by Lavenant, Zhang, Kim, and Schibinger, which I think is very beautiful mathematically. So you have an estimator, so you want to recover the stochastic process, and the estimator you have, or will be the recovered stochastic process. It will be chosen so as to minimize a certain energy, which is the sum of a data fitting term. Here, this is the log likelihood of the observations under the marginals of the stochastic process that we recover R, plus some regularization term, which is here the relative entropy between R and the law of the Brunel motion, so the Wiener measure, at diffusivity level tau. So in this last section, I will put a little bit less detail so that we go to the heart of the matter more quickly. So this is the objective function that they propose to minimize, and they have proved that if you do that, and the number of observations goes to plus infinity, then you have consistency in the sense that you are able to recover a certain class of diffusion process by solving this problem. So R will, if you have a sufficient number of data, asymptotically, R will converge to the law of the stochastic process that has generated the data, assuming that it is of Ito type, so a drift diffusion process with a drift which is given by a gradient. So we'll consider now just the numerical resolution of this problem because this seems very challenging. So the first idea, which I think can be traced back to this paper by Benamou, Carlier, Di Marino, and Nena, is that we can decompose the relative entropy in path space by having, in terms of some entropic optimal transport with some cost Ci, which I will not really describe. These are the log heat kernels, and some entropy. Okay, so we can decompose the first problem, which has this data fitting term plus the relative entropy, into this new problem, which will be equivalent. And now what the new variables are just the time marginals of the stochastic process that we want to recover, mu1 to mu t, we are assuming we have t time marginals. And we can decompose this new problem into a function over the space of probability measures plus some entropy term. So here, so here what's key is that we have a new objective function which has some entropy with diffusivity level tau, and some function which is smooth, because here this is entropic optimal transport, so this is smooth, it has the regularity that is needed to have a well-posedness by the previous results. And if you want an interpretation of this problem, so in blue, these are the marginals that we want to recover. In red, these are these observations. So we want the observations to have a high likelihood under the blue marginals. And these terms will penalize how much successive time marginals differ in terms of this entropic optimal transport cost. And we have this additional entropy term. So this is the optimization problem we want to solve. And we will apply the same kind of technique, which is to discretize the marginals with particles and run noisy gradient descent on G, where the noise will be used to cover this third term, which comes up naturally in the problem. And we get this kind of dynamics. So here, this is just a 1D example. Of course, the biological applications are in a higher dimension, but we see that we have this sort of diffusion in path space, which in the end converges to this mean entropy against the Wiener measure. And here it looks, it solves this trajectory inference. So I joined the all points by some Brownian bridge, because this is what the theory tells us, that we should join points by Brownian bridge. And in the end, we see that somehow we converge to some trajectory inference. And we have some guarantees for these dynamics, which are analogous to the previous theory that I've shown, that it is well posed, because entropic optimal transport has the required regularity, and it converges to the unique global minimizer. So here, the proof is a slightly more subtle because this function G is not convex in the space of probability measures, but with this additional entropy, it will be convex. This is the first remark I've made in my talk, that if you add sufficient entropy to entropic optimal transport, you get some joint convexity in all the marginals. And so what we need to do is to have stronger noise at the beginning of the dynamics and make some simulated annealing. That's where the theory of simulated annealing can help us to study this problem. And you make the noise decrease towards the level 2. So that's what is covered by the theoretical guarantee. Although in practice, we observe that just fixing the noise level 2 throughout does not lead to any disagreement. So we have, you can check maybe the paper if you want to see some validation in high dimensional problems, just to make sure that these kind of algorithms have a nice performance in practice. So this I will skip and jump to the conclusion. So my general message is that there is a nice interlink between entropic optimal transport and this kind of dynamics, which are called mean field Langevin, these noisy particle methods. And here, these are the references on which this talk is based. The one on barycenters is in preparation, and all the other ones can be found online. So that's it.
Thank you also for sticking with schedule. So are there any questions or comments for Lénaïc? Giuseppe?
I understood the convergence of the the minimizer. How do you
Yeah, so that's the part which is still work in progress, I would say. So what we already know is to go from this dynamics to this one. What we already know, although it's not really written, but it can be inferred from the literature, that the stability of G under sampling is what matters to get rates of convergence. So let's say in our case, G is entropic optimal transport. So we have very, very nice results, for instance, by Philippe and Cotar, where we know how much it like how fast this potential converges to the limit when we sample from independent particles. And so we can get convergence rates in bounded time. Let's say I fix time interval 0, capital T, and then we would have parametric rates. So we know in some measures of distance between UT and its empirical version, we should not be Wasserstein, of course, but some smoother measures. We would have like a rate of convergence for the 1 over square root m. But the idea is that usually when we have exponential ergodicity, we can make stronger results about uniform propagation of chaos, so uniform error bounds in time, because we also have on the other side this exponential relaxation of the dynamic. So the idea would be to combine these two to get uniform in time error estimate, but that's not at all, not ready at all.
Other questions? Well, if not, let's thank the speaker one more time.
Maybe just one question. For the first part, is it possible to consider also unbalanced flow, so to also modify the amplitude of the particle, and would it improve the results in practice or in theory?
So, so the question would be, do we have convergence? Okay, so my view of this kind of dynamics, when we want to optimize a convex function over the space of probability measures, either we use noise to get convergence, which is what I presented today, or we use unbalancedness, which is what you presented. For the unbalancedness,
can you do both at the same time? My question is, can you do both at the same time?
Yeah, so I was about to say that. So we can do both at the same time in theory. The issue is that when you get, like, it's not clear, like I've tried some numerical experiments, it's not clear what we get. Like in theory, what you see easily is that since you add a degree of freedom in your dynamics, you'll get an energy decay which is faster than this one, so the same proof will go through. Okay. Now the question is that the issue is that you'll also get, like when you want to implement these dynamics, you would need to add some density estimation, because the Fisher-Rao gradient of the entropy is just the logarithm, so you need to estimate the log density and follow, like, to add this level of variation, which is not clear in practice whether, like, I think that will kill the I think this will need the exponential dependency in the dimension, because you need density estimation to discretize this dynamic. So the difference will be seen when we'll finally understood more precisely the discrete the rates of the discrete dynamics.
Okay, let's move on and let's thank again the speaker. The last speaker this morning is Enrico Facca. Enrico was the Giorgi postdoctoral fellow here in Pisa for 2 years, and then moved to INRIA in Lille. He's going to talk about the use of interior point methods to solve optimal transport problems.
So thank you, Michele. Thank you, everybody from here, and also the organizer for reorganizing this nice meeting again. As the title says, we'll talk about some what we have done together. I've done together with Andrea Natale at INRIA Lille as me, and Gabriele Todeschi at the University of Grenoble, and also Michele Benstein about finding efficient way to solve the L2 optimal transport problem. Just a warm-up slide which problem I'm addressing to. I refer to the L2 problem, the optimal transport problem, where the cost is the quadratic distance. And in particular, I will set our problem in a domain that is existing R at the some dimension, but just R1 and 2 and 3. In particular, just R2 and 3, because I will work on the optimal transport, let's say, from continuous to continuous, and trying to find efficient way to solve it, the PDE counterpart of this optimal transport problem. And because you probably know very well that in this setting, this problem can be written in this form, in a dynamical form, where instead of looking for static function, you look for a density rho that is interpolating the initial density and the final configuration. And you want to find an interpolant that is, for case of Gaussian in 1D, this nice interpolation between Gaussian. But you have also to find the velocity field that is moving this density. Sorry, okay. The velocity field that is moving the density, that is varying again in time and in space, and is also orthogonal to our domain, and it's solves this optimization problem. You want to minimize the total kinetic energy of the system under the constraint of the continuity equation. So this is our problem. I just rewrite it again, what we are looking for, this curve of density and the velocity field. We want to solve this constraint optimization problem. You start working a bit, and then you realize that actually the direction, the velocity you have to follow is just the gradient of a potential that is varying again in time and space. So you can rewrite a bit the term, and you have just to look for two unknowns: the density, the curve, and the potential, which is giving you the gradient of the direction. Then you do some optimization, you make some derivatives, you write the analogous of the Euler-Lagrange equation for this optimization problem. Therefore, this problem read as the continuity equation and then this Hamilton-Jacobi inequality. But moreover, we also add an additional variable as a slackness variable that somehow saturates the inequality constraint that we have here. And there is also a complementary condition between the density. It means that when one is 0, the other has to be positive and vice versa. And we wanted to solve this non-linear equation. And when we solve this, the answer is we wanted to find this phi, the potential, the density, and the slackness that lives in some finite dimensional space of functions. defined on the time-space domain. And in particular, this n refers to the number of degrees of freedom we use to discretize this function space. And for this problem, you know that the number of degrees of freedom will scale as the inverse of the spatial scale, raised to the dimension, and divided also by the time space. So you really see that dimension, the n is really growing really fast because we're going to use some finite element method, finite volume. So the dimension of this nonlinear equation will grow really fast. And when we want to do this, there are essentially three questions we have to ask ourselves. The first is, what is a good time and space discretization? Because we might choose different approaches, different finite dimensional spaces. The second is how we solve this discrete optimization problem, because it's highly nonlinear in this case. The third is how the computational cost scale with respect to the n. This is the most important things, how much the computational cost is scaling when we look at a finer problem, essentially when we start approximating the real problem. So let's start with trying to answer to the first question. Some work was already done, well, in the very first paper by Benamou and Brenier, of course, and then in a work by Papadakis, Peyré. They also realized that a good discretization scheme might be to use stagger grid in time. And I will explain later immediately what is stagger grid in time, and because this approach used also by the collaborator Natale and Todeschi in this recent paper, essentially with respect to time, we discretize our time interval between 0 and 1 in some slots, with k is the number of time steps, but the potential and the density and also the slackness variable are defined in slack times, in between, let's say, between two densities. And so, under this stagger grid scheme, our approximation of the curve of the potential is going to be a linear interpolation of these rho 0, rho 1, and rho 2. Well, there is number. While the density is going to be interpolation of the initial and the final, and also the solution we are looking for, and also the linear interpolation of the slackness variable. The potential and the rho will belong to some finite dimensional spaces, and then there is a second choice. We have to choose which finite dimensional spaces, and Natale and Todeschi use finite volume discretization using 2-point flux approximation, where essentially the function at each time stamp is discretized as a piecewise function on each cell. This is the space, it means piecewise constant on the triangulation for the density, while for the potential variable, the phi variable, they use a second grid that is finer. Essentially, each cell here is subdivided in further 3 cells. Why did they do this? Because essentially what they noticed that when we were trying to discretize the problem using the same grid and the same functional space, they were looking at some checkboard instabilities. And what they realized that when they were using, let's say, a richer space for the potential using this double level grid, this instability disappear. And so regarding the first question on what might be the good discretization for solving this PD is stagger grid in time and 2-level finite volumes. Let me also remark that these checkboard instabilities appears also in other optimal transport problem when you try to solve it. For example, the optimal transport problem where the cost is equal to the distance, just the distance, and also shape optimization problem. And probably Professor Bouchité will speak about this on Friday, I think, something connected. But anyway, when you try to solve it, this instability appears, even if the reason exactly why this is happening and the solution, for example, why when we got a richer space on the potential, this instability disappear is something that is not really clear so far. So this is for the first question, good discretization space. The second question, how to solve the discrete optimization problem? The answer here is interior point method. Essentially, we have the variation, the de-optimization problem, the discrete nonlinear equation, The interior point method acts to essentially to add a logarithmic barrier that is scaled with a relaxation parameter epsilon, which is essentially the standard of interior point method. There is a huge theory explaining why this is the right barrier. They talk about self-concordance property. This is like one of the most used approach for solving this nonlinear optimization problem. And the idea that when you put the epsilon barrier here, this epsilon appears here in the complementary slackness condition. And the continuation method behind the interior point approach is the fact that you progressively essentially solve this nonlinear equation using Newton method, and then you progressively decrease the epsilon, so you want to recover the solution of your unregularized problem. So epsilon goes to 0. So convergence is this, proving convergence for this approach is particularly difficult. There are some work on Hugo Lavant on some convergence in gamma convergences, relatively weak with respect to what we would like to have something stronger. So we will just limit ourselves to see what happens when we look at the experimental convergence. Experimental convergence means that we take a problem where we have an exact solution and we just compare how the error decays when we enlarge our finite dimensional spaces. And here is an example of the problem we took. Is just the translation of a density, but is a compact that is compactly supported. That typically is more difficult to handle from the numerical point of view, because here the density goes to 0, so it's always much more difficult. So this is just the curve that the interpolating curve. And here I reported a table that is just the error when the epsilon is progressively reduced. And here, moving from left to right, you see that we are increasing the size of the n, which means that are enlarging our finite dimensional spaces. And the factor here is a factor 8, because the problem is 2D, and then there is time, so it's a factor 8 at each time. And you see that somehow reducing the epsilon, we got some saturation with respect to the error, because essentially the error given by the approximation of the interior point is somehow reaching the approximation we have on the problem. But in the same goes here, but you see that the saturation starts later. The most important things is looking at the number at the bottom, where we say, okay, we reach our optimal solution, and look at the rate of the error. The most important thing is that since we are refining in time and space, we will expect that the error half at each refinement. And as you can see, more or less, this is what we get. So in this experimental, we get a good approximation. And so is another case with the other density, where we use is essentially the transportation of a density into a compressed one. So there is a compression of the densities, and this we will see later make the problems also more difficult. But again, the most important things here, with some oscillation here on this value, you see that the error is halved, increasing the size of the problem. So we have some clue that the approximation, the algorithm is working well. The third question I pose is how much time does it take to solve it, and what we have to do. So here we have the the relaxed optimization, and I say we are going to use a reduced epsilon and solve each nonlinear equation using Newton. But what does it mean using Newton? Well, this is the nonlinear equation. We have to assemble the Jacobian of this nonlinear equation, find the direction. Is Newton method, everybody know. And for this case, solving this linear system here reduce somehow to solving this saddle point linear system, where the operator here A, B, and Cn are written essentially are the finite dimensional counterpart of this operator here. This weighted Laplacian with respect to the density, this directional derivative, let's say with respect to the gradient of the potential, and also there is this relaxation term C, because it's somehow scaling with like epsilon divided by rho squared. And also in the next slide, I will drop, let's say, the dependence between the n dependence to say that it's discrete, somehow confusing a bit the linear operator and the matrices. I hope that you will follow me. It should be easy, but just remember this. There will be the matrices. So we want to solve this saddle point in a system with these matrices. And what we want to do is preconditioning. What does it mean, preconditioning? It essentially means to, instead of solving this difficult problem because it's sparse, but it's really large. So we want to find a preconditioner. What is a preconditioner? Is a linear operator which somehow is approximating the inverse of the Jacobian. The Jacobian is these block matrices. And where the application of the preconditioner, which means solving these a linear system of this form, is easy, is cheap, is scale. We would like to have it linearly with respect to the number of degrees of freedom we have. And so now a crash course on saddle point preconditioner, really crash course. A good one option you have for preconditioning this linear system is using, I will call it like primal, forming the primal Schur complement. Essentially, if you use this block diagonal system where here you have this operator with this formula, you see that inverse of C is extremely easy, but what you get here in the primal Schur complement, that is something that we have to invert, I mean, solving a linear system with this matrix, might be particularly difficult, because if you look at the operator that are behind, what you get here is a sort of weighted Laplacian system, because divergence and gradient here and a strange weight here, you have rho. But let's say that the bad guy here, also with respect to the epsilon, it's this, because you have an anisotropic term divided by epsilon. So you have an anisotropic term that is exploding, and this is particularly bad for multigrid solver. I mean, when you have anisotropy in weighted elliptic equation, might be really difficult to handle, and here is somehow going to infinity or when. And also there are extra terms. So we try to use this, we use multigrid solver to tackle this linear system, but they were suffering. So a second approach to, again, to preconditioning to this linear system is like to move to the dual Schur complement, which essentially represents to reduce in the phi variable and solve in the rho variable. And I put here the inverse of A in green because that there already exists technology to solve in this weighted Laplacian system efficiently in parallel. The technology is already there, but the bad guy here, because it's in red, is the dual Schur complement, because essentially the inverse of the Laplacian is essentially a dense operator, and we cannot form the dual Schur complement, and so neither inverted. So we have to find a clever strategy to, remember, just apply the inverse of the dual Schur complement. But after a really long time, we realized that there exists this identity, just a differential identity if you just take the operator that I've written here and you just assume all the regularity you want. Because we are in a preconditioned regime, we have just to be close to what we really are dealing with. You have this sort of commutation between operator A and B. There is also a transport appear, and you have some extra, let's say the commutator we might see. So some extra term, and you see that here is appearing the continuity equation. So we might say, okay, we are in a preconditioning regime, and since the nonlinear equation is one of our nonlinear equation, we can just drop this term. It's legitimate. And then we are left with an extra term where the Hessian of the potential is appearing. And so we would like to say to kill it, to drop this term. We might think that this is reasonable for example, the fundamental solution of the optimal transport, that is just translation in some cases. And there are some work, for example, from Maria Colombo, and also from Fatim Max yesterday, just trying to estimate, let's say, the upper bound of the Hessian here. So essentially, probably theory is giving some answer to this problem if we can just drop this term. Now we just drop it. There are maybe further questions to handle it better. So we are left with this approximate identity of operator. And then if you multiply both sides by B A minus 1 and you add C, this is the, we get with an approximate version of this dual Schur complement. And then with some essentially trivial manipulation now, the inverse of the dual Schur complement can be approximated with this, with let this appear, and then we get this with some factorization, okay? What we are left here is just the product of sparse operator, and when we have sparse operator to invert, we are happy, because there are efficient multi-grid solvers, just algebraic. Maybe we need to understand better what is these guys from the differential point of view, and optimal transport mobile will provide the answer. But already with this sparse operator here and this sparse operator here, we are rather happy. So numerical result into D, the same problem. And here now I reported how epsilon is decreased, and here the total CPU time for solving the total Newton cycle. And you see that unfortunately in all cases the CPU is increasing with when epsilon is decreased, but it's somehow something classical in interior point method. This linear system become more and more conditioning. But you see that the most important thing, let's say the bottom line with respect to the CPU and also the total CPU, is scaling more or less slightly more than linear with respect to the number of degrees of freedom that is multiplied by a factor 8. And this is, what does it mean? That this is a second example, sorry, the one I presented before, where, as I say, the Hessian, the Laplacian is not 0, so also the Hessian. And that, so when I drop the term with the Hessian, this is not actually 0. But you see that the CPU again is scaling pretty good with respect to the number of degrees of freedom, so slightly more than linear, the CPU time. So summarizing, I got to the end. This was the optimization problem that we relax using interior point barrier. This is the RAX optimization problem, and this is the linear algebra problem that is at the bottom of this, but is the real bottleneck of the problem when you want to solve the continuous to continuous problem with the quadratic cost. The 3 questions I made, discretization, staggered grid in time, and 2-level finite volumes. Solving the discrete problem. Okay, let's use interior point method and the preconditioner based on this identity. And the last, the computational cost, we might say that using this precondition is slightly more than linear with respect to the number of degrees of freedom. So we are really happy with that. And so if I have time, I don't know, just looking a bit forward, don't know. Wrap? Quick. Okay, discretization, understanding why this instability occurs, which is the good recipe to understand which is the best one. Solving a discrete problem, I use this approximating equality. We would like to understand better if we can just drop or get some other sparse term for essentially this operator here, if they are small, if they are sparse. Understand it better instead just of quitting them. This is not. And computational cost, well, we want to move, of course, in parallel, and this is feasible with current technology. Just multi-grid solver, algebraic are already there, but will take time to code, of course. And maybe to use some predictor corrector approach from interior point to avoid oversolving when we solve the Newton system. So I'm done.
The questions for Enrico?
I'm just curious about the choice of minus the logarithm as a penalization or as a function for the interior penalization method. Is this standard, or do you have some flexibility to use other kind of functions?
There are theory about using different barrier functions. Maybe someone might think on entropy regularization, but it's this standard function used in interior point approximation, because actually at the very end you see that you have this nice relaxed complementary condition, so you can also play with this also in the predictor correction approach. And it's a self-concordant variant, so you have estimate on how Newton is converging. I mean, there is a huge theory that we want to use, and so we stay with that, but there is no problem in that. Actually, I think I forgot to mention, yes, that from the linear algebra point of view, if you add some functional with respect to the density here, it will appear here and here. But for all the computation I presented will not really be affected from the difficult part, like the swapping of the operator, will be still there. So we can change it rather easily and then see if we gain something from, well, whatever, the computational point of view, or if you want to model different problem.
I have a comment. You didn't mention it, but I'm sure you thought about it. The checkerboard instability in the non-staggered discretization suggests that maybe some kind of in-soup condition should be satisfied, Babushka-Brezzi type condition. Do you want to comment on it?
Yes.
Oh, there you go.
Essentially, I just see that anytime you have to solve some problem where there is some compliance optimization, essentially you have some density that has to be positive. So that is really a nasty part in the sense that typically the density that you look in theory is, you say, is bounded from below, but here is more difficult. It's not bounded from below. It's not an Hilbert space. We think that there might be some non-linear in soup because unfortunately here this is non-linear. We might think to look at the linearized problem, but I don't know the answer. I'm asking to the audience, and it's probably there what we have to look for, but honestly I don't know the answer yet.
Okay, one quick question because I'm told that we need to hurry to the canteen because there will be long lines today.
Thanks. So I had a rather basic question, and actually it may already be answered in Jan and Benu's paper, I'm not sure. So something else that you could do if you wanted to compute the discretization of the OT path is you just compute the optimal plan between the initial and terminal measures, and then you do geodesic interpolation of a bunch of particles.
I think that you will miss the time dynamic in the middle. You don't know exactly the speed to take in the between because you need the full evolution in time of the potential.
But is it not the case that the particles move at constant speed in intermediate time?
No, the potential is varying also in time.
I see. Okay, that's the thing you missed. Thanks.
Let's thank the speaker, and in fact, all the speakers in this morning session.
Let us start the afternoon session for today. So let me introduce Philippe Rigollet from MIT.
It's a nice environment if you want to spend some time abroad a little bit. So today I'm actually going to talk about some joint work with Sino and Anya, who are respectively a graduate student and a postdoc at MIT, and also some work I did in the spring while I was visiting Paris with these collaborators. Yeah. So let me start by motivating a little bit of what I'm going to talk about, in particular with variational inferences from the perspective of Bayesian inference. Right, so I'm going to take a prototypical Bayesian statistics question, which is Bayesian logistic regression, where the goal is to essentially predict y's, which are binary responses, think cat or dog, from x's, which are features. So think of an image and you're trying to predict. And so since y is binary, y given x is also binary, and so you don't have any modeling to do. You know it's going to be a Bernoulli random variable, and all you have to do is to model what the conditional expectation is. And that's what the logistic model is. It's telling you should take it of this form, so just this simple nonlinear transformation that takes a linear function of x and basically maps it into the interval 0, 1, so it's a valid conditional probability for a Bernoulli. Okay, so that's the model, and so how would you fit it? Well, if you were a frequentist, you would write the likelihood, right? So the likelihood of beta is essentially the joint probability distribution of your xi, yi's evaluated at your observations, xi's and yi's. This is what it looks like. And you would maximize it over beta. But if you're Bayesian, what you're going to do is you're going to actually form the posterior, and there's a simple rule to do this that comes from Bayes' rule, and it says the posterior distribution, what you do is you assume that beta itself is actually drawn from some prior distribution, let's call it nu, and then you just multiply the prior by the likelihood, renormalize, and that's your posterior distribution. So that's a distribution of the parameter beta, and you should think of this distribution as being essentially concentrated around the most plausible value for the beta that you have, okay? As n goes to infinity, this thing should contract to a single point. And if n is large, it should still be pretty concentrated. Right, so that's the object of interest from Bayesian inference, and people would like to extract some summary statistics from this. Okay, so this is what this is the kind of objects we're going to be talking about. This is just something for you to keep in mind. So, I'm going to write pi of beta as e to the minus v of beta, and this v just takes this particular form, so it's really just the log of this numerator. But notice here that I actually just write a proportionality coefficient. I don't know what the normalizing constant is. It's this complicated integral d beta, and I just don't know what it is. Okay, so when I'm going to have access to this, like the analytical access that I have to this pi of beta is really just the numerator, but I have no idea of what this log partition function actually looks like, or this partition function looks like. Okay, and in particular, if nu is convex, for example, you take a Gaussian prior, something that will force your betas to be somewhat, constrained to not be too far from the origin, then this whole v of beta turns out to be convex, right? You see, you have v of beta turns out to be concave. So you have minus v of beta. This is concave, so this is log of e. All right, so this is linear. This is convex. This should be convex, so I probably missed the negative sign somewhere. Okay, but it's convex if you have logistic regression. Okay, so once you have this, the goals, so looking at a probability distribution in high dimension is not very convenient, so you would like to take some summary statistics. The first two things we can think of are taking its mean, and it's so-called Bayesian Bayes estimator, so it's just the mean of a posteriori distribution, and it's optimal in a decision theoretic sense. This is the best. If you have to output one single point, this is going to be the most precise you can output. And you might also find what's called credible sets that says, well, maybe some high probability sets where you know that most of the mass of your posterior is concentrated. So the typical choices, of course, you can do anything you want, but the typical choices are ellipsoids or just boxes, high-dimensional hyperrectangles. Okay? So this is the kind of things that people want to do with this posterior. Okay, so in a way, the posterior is a means to an end, and the end is to find one of those two things. So from now on, I'm going to just forget about this beta. It's kind of weird to have beta as my main variable, so I'm going to call it x, and I'm going to assume that since I don't know the normalizing constant of pi, I only have access to grad v, Hessian of v, and higher derivative of v. Those do not depend on the normalizing constant. And if you look at the Bayesian example I gave you, those are certainly things you can actually compute, right? They don't require the normalizing constant. All right, so that's what we want, and we want to be able to get those summary statistics. So there's two ways to do this, two paradigms. And the first one is MCMC, Markov chain Monte Carlo. And the idea is to say, well, let's just sample a bunch of observations, x1, xt, that are distributed according to a distribution close to pi, and then just take their average to have an estimate for the mean a posteriori, take their sample covariance matrix as an estimate for the covariance matrix of this posterior distribution. And the way you get those x1, xt is by running a Markov chain whose invariant distribution is pi. And obviously, say things based on Langevin diffusion will only require knowing grad log pi, which is v. All right, so that's the first and maybe most traditional setup, right? I mean, computational Bayesian statistics is a lot about computing this kind of things. But there was this new paradigm that came maybe almost 20 years ago now from machine learning, and it says, well, if you're going to only extract simple statistics from pi, might as well just try to approximate pi by something simple, say a Gaussian, for which, well, the parameters are going to be the mean and the covariance, and so those things can play the role as proxies for the mean of pi and the covariance matrix of pi. So just one slide on what MCMC looks like, what the current research looks like. So as I say, you can write something based on a discretization of the Langevin diffusion. There's tons of algorithms. This is actually a very active research field right now, mostly under the impetus of Arnaque Dalalian in 2014, who wrote a paper that said, well, all these toolbox that you have for optimization, you can apply it for sampling and derive some finite sample algorithmic bounds, which sort of break away from the traditional continuous time asymptotic analysis that you see in stochastic analysis, so in probability, I guess. Right, so, and the kind of results you'll see look like, well, if, V has a well-conditioned Hessian, so, and the eigenvalues are between 1/2 and 2, say, then you can approximately sample from pi after essentially order of dimension queries to grad V. Okay, so you need only to access grad V, and those are the kind of results that people have in mind. When it comes to variational inference, there's really nothing like this. Okay, so people just apply it and they say, yeah. Yeah, so think total variation. I'm trying to be vague here mostly. There's like anything you want is out there really now at this point. And this d-dependence can be really, I mean, people are fighting over this pretty hard. But, you know, I think d to the 1/3 is probably the best that can be done right now. And of course, you can pull on the assumptions. I mean, there's tons of research right now. All right, so in variational inference, you want to approximate pi by something in a simple family of distribution, right? Let's call it script p. And some common choices that people have used are product measures, right? So this is called mean field variational inference. Why product measures? Because once you have a product measure, you can form this credible box, right? You have one marginal for each of the coordinates, and you can actually build this credible box. So for each coordinate of this parameter beta that came from the logistic regression, you could actually have a confidence interval. If you think you're practitioners, this is probably going to be enough. You don't need to really understand the correlations. And you can also think of Gaussians, as I mentioned, or mixtures of Gaussians. And in this talk, I'm mostly going to talk about Gaussians, and I'm probably going to run out of time to talk about mixtures of Gaussians, but you know, you never know. Maybe I'll be as fast as Gabriel this morning, who knows. All right, so so a classical way to do this, you probably all know this. There's actually a way to do this that was never framed as variational inference, but if I give you a distribution which is, say, log concave or e to the minus something, and this something grows with n, then you actually use the Laplace method, right? The Laplace method tells you that this thing will look like a Gaussian whose center is the minimizer of V, and whose covariance is the Hessian of V at this minimizer. Okay, so mu bar here is the argmin of V, so that's the so-called maximum a posteriori. That's the maximum of pi. It's a nice thing to do because you only need an optimization algorithm to find this. And then to find the associated covariance matrix, you just take the Hessian of V at this point, mu bar. Okay, so that's one way to do this, and that's, you know, variational inference is trying to go beyond this, but this is actually a pretty serious competitor, in fact. So for Gaussian variational inference, variational means we're trying to solve an optimization problem. We're not just throwing one Gaussian and say, let's see how good it is. Let's just try to find the best Gaussian, right? The Gaussian is the closest to pi, and the traditional objective function that people have put forward is the scale of something with respect to pi. So now you could question this, and actually there's tons of research about changing this to maybe some, you know, Renyi divergence or, you know, other measures of divergence between p and pi. But it turns out that this one is extremely convenient because if I want to start taking gradients, I only need to have access to grad log pi, which is the only thing that I have. Okay? So this is the kind of thing that I need to be able to solve, and I'm not inventing this scale, and you probably recognize this scale to pi, and there's not going to be too much surprise there. So I'm going to try to minimize this. So the talk will have two parts. The first one will be computational, so how to minimize this, and as the title says, I'm going to use a Wasserstein gradient flow to optimize over this space of Gaussians, this objective function, and use our pretty classical theory to obtain some convergence guarantees. And the second part is the most recent one I did with Anya Katsevich, which is why would you even do this, right? Is the closest Gaussian to pi actually a reasonable estimate for pi, right? And that's, in particular, does it do better than just the simple Laplace method that we all knew? Right, so that's the second thing. So the way we're going to do this is talk about Wasserstein gradient flows. So the way you think about Wasserstein gradient flows depends on where you're coming from. I'm a statistician, so my main connection is to probability, and I think of Wasserstein gradient flows in this following way. So I look at a Langevin diffusion. I know that its invariant measure is going to be the pi I want, e to the minus v. But if the temporal correlations dependence of this process, and I only care about the evolution of the law of the marginals of this process, I know it's going to follow the Fokker-Planck equation. So that might be your point of entry to Wasserstein gradient flows. All right, so that's just the associated variation for the marginal pi t. And of course, we know there's this, and so basically this describes a curve, sorry, in the space of probability distributions, and we know that somehow this curve converges to the pi we're interested in. And so we know that in fact this perspective can be also taken. You can also take a perspective from of the Wasserstein gradient flow, which was put forward by Otto and made formal in, of course, the famous book of Ambrosio G. Savare. And the goal is to, and the description here is to say that if you have this like deterministic movement applied to xt, which is grad v of xt minus grad log pi t of xt, where pi t is the distribution at time t of xt, then you have this completely deterministic evolution equation that actually describes the same curve in the space of probability measures. Right, so now you have this deterministic trajectory, and if you're a practitioner, it's actually very enticing, right? You could say, well, okay, how do I replace Langevin if I want to sample using this deterministic thing? I should have much more regular trajectories. I don't have to inject noise in there. It should work better. And people have actually tried to do this, so let me open a little parenthesis and tell you what is the current, top choice for practitioners to try to implement, like the actual Wasserstein gradient flows as an alternative to, of the KL as an alternative to Langevin diffusions. And so the main issue, obviously, here is that you actually need to know what pi t is at any given point in time, right? You need to find what this grad log pi t is. That's the one that's coming from the entropy part of the KL divergence. And the idea is to say, okay, let's just evolve a bunch of particles that should be giving me an idea of what the distribution pi t is, right? If I have enough of those particles, they should look like pi t. I should be able to extract. The problem is that it's hard to just estimate the full distribution, right? I mean, I could form some sort of a kernel density estimator of the of pi t, maybe take its grad log, do something like this, but this is not what people have used. And the main direction is, the main algorithm right now is called Stein variational gradient descent, or SVGD, and it goes as follows, okay? So this is the evolution I'm trying to replicate. And the first thing it says, okay, I don't know what this grad log pi t is, so what I'm going to do is I'm going to project it on something that I can estimate well. And this something is essentially some RKHS, a reproducing kernel Hilbert space. So the way it goes, it says, okay, I'm going to take this kernel, k of x, y. If there was no pi t here, you should think of k of x, y as being, delta of x is equal to y, right? It should really be something that forces x to be equal to y, and then it would be the same thing. But then there's this d pi t, and the kernel is something that's concentrated around delta x is equal to y, but in fact, it's something that's like more of a Gaussian in a way. All right, so, the d pi t here might seem weird because you're actually projecting on the different reproducing kernel Hilbert space at each time point. But, since you know that the tangent plane, the tangent space is L2 of pi t at time t for Wasserstein 2, it's not so surprising. All right, so let's see how, if you think that this approximation is correct, which essentially thinks that this gradient is actually smooth in a way, then let's see what that brings you, all right? So I'm going to unpack my grad log as the grad pi over pi. And now I see that there's this nice cancellation that's happening. So it's just k grad pi, and now I apply the divergence theorem, or integration by parts, and I push the grad onto the k rather than onto the pi. Why do I do this? Because now I have an integral d pi t, and this integral d pi t is really an expectation with respect to pi t. And as I like to tell my students, 99% of statistics consists in replacing expectations by averages and doing something fancy. Of course, we've done something fancy before, but really we just replaced the expectation by an average, and the work was to make the expectation show up. And so we replace it by this average over those n particles that evolve, and now that gives us a way for all those particles to interact together, and that gives us a system of interacting particles. For each particle j moves by interacting with all the particles I through this gradient of a kernel. Okay, so that's it. That's what SVGD is about. And then you discretize this, and that gives you SVGD. So this is a very appealing process, complete alternative. You know that if n goes to infinity, this thing will actually track precisely the trajectories of Langevin or of Fokker-Planck in the space of probability distributions. So it's very, conceptually for us, it's very new. It's completely deterministic. The only randomness that comes into play is the initialization of your particles. Everything else is a deterministic movement. Very elegant. And the downside, though, is that you have to choose k. So, I dropped on you this like Gaussian kernel, but, why? Also, it doesn't really scale for d larger than 3, which, is a serious problem. The third problem is that, so it's implementing VI. So somehow you're constraining your gradient flow to be something, right? You're constraining the gradient to actually be projected on these RKHS as you go, but you've lost complete track of what was your implicit bias. At the end, you're going to have a distribution which is not pi itself. It's some distribution that's like close to pi in some space, but you have no way of finding out what this P class of distributions in which this actually belongs. It's just a sequence of push forward by smooth maps, really. And so that's, I think, from a conceptual perspective, it's a big downside. You don't really know what it's doing, and actually, you know, it's not always converging. In fact, because you're projecting at some point, you're going to want to go in the null space of this projection operator. So your gradient is basically going to stop moving, even though you're not at optimality. So I think the reason why it doesn't scale for large D is that it's too non-parametric in a sense. There's just too many moving parameters. We're actually trying to model full classes of functions. That's what reproducing kernel Hilbert space theory is for. And this just does not scale to high dimensions. That's just the way it is. And so what we're going to be looking at in the rest of this talk is a parametric alternative to this, right? Can we implement Wasserstein gradient flow with only having like finite dimensional parameters, right? That's what parametric means, as opposed to non-parametric, where you have infinite dimensional parameters, function spaces. And so the idea here is going to be evolving a Gaussian, right? The first parametric family you can think of is the Gaussian family. And so really, I'm going to just try to implement a Gaussian VI by evolving a Gaussian. Right? So let's see how we would start doing this. So look, let's go back to Langevin. All right, so Langevin goes like this, and when you look at Langevin, you can actually write the mean of xt at each time t and the covariance at time t, and you can write a system of coupled ODEs that tell you how mt evolves and how sigma t evolves according to time. Right? It's not very difficult, and you see, I mean, it's just this equation. The identity comes because, you know, gradient of log of a Gaussian is just, you know, simple, or Hessian is something simple. So there's this kind of things that show up, but I mean, it's a simple, you don't have to actually parse the details. It's just a simple system of coupled ODEs, one for the mean, one for the covariance. And if you look carefully, there's these expectations here with respect to xt, all right? So those are integrals d pi t. So I did not clean my problem at all because I don't know what pi t is. I don't know what the evolution pi t is of the law of xt. So I don't know what this thing is. And so, you know, you might actually say, okay, well, if I don't know what it is, one thing pretty stupid I can do is, so I don't know how to compute those expectations. So can I just replace this xt by the Gaussian with mean mt and sigma t at current time? All right, so let's just do this. So this is a principle that does not have a name that comes from, you know, Kalman filtering, and I would call it, if I had to, I would call it just pretend everything is Gaussians and pray it works. All right, and so this guy Sarka implemented this heuristic without any justification because, you know, what else could he do? He didn't know what how to compute those expectations, so he just pretended it was Gaussian, and he just said, okay, let's implement this to track the Langevin. So it turns out that this does yield a Gaussian approximation. Of course, I'm evolving a mean and a covariance, so I can form the distribution that has this mean and covariance. So, you know, unfortunately for Sarka, this is obviously not the mean and covariance of Langevin as you go. But it actually is something that is meaningful, and that's what we're going to go. We're going to try to understand if this evolution makes any sense and if I can actually describe the curve of Gaussians within the space of probability distributions that this describes. So what we prove is a counterpart of this JKO result. So JKO tells us that, you know, if you look at the law of pi t of the Langevin diffusion, it's the gradient flow of the KL on the Wasserstein space. Right? So hopefully everybody here is familiar with what this statement means. And what we prove is the same result with this additional condition, which is just constrained to lie in the space of Gaussians. Okay, so it's basically a constrained gradient flow where I'm only evolving Gaussians to Gaussians. And Gaussians are nice because the tangent plane on the subspace of Gaussians are just affine vector fields, so I can describe it in terms of the vector field or in terms of just actually constraining this. It's completely equivalent. All right, so the picture you need to have in mind is the following. Langevin just moves in the full space of distributions, and this thing is the Bures-Wasserstein space of Gaussians, right? So that's the name, and hence we call this procedure Bures-JKO. And Bures-Wasserstein is simply something that's this process, or Sarka's process, that's supposed to just move to something in the space of Gaussian. Is going to converge to some Gaussian, and hopefully we hope that this Gaussian is the argmin of the KL. Okay, so in practice, how do I implement this, right? So how do I implement Sarka? So Sarka proposed some implementations. We essentially follow the same recipe, so there's no novelty there. So, you know, you have a system of coupled ADEs. Numerical analysts have done this much better than people in machine learning for this kind of simple thing. So you just apply Runge-Kutta, And to compute the expectations, those are Gaussian expectations. So my collaborator, Marc Lambert, wanted to use cubature rules. It works well. I trust them. You can use whatever you want. But basically, this is how it goes. Okay, and you can show, so if this is the posterior, this is actually a logistic posterior. And you can see how this Gaussian evolves, and it's just going to have its mean that goes where it should be, and then the covariance is going to align well with the main directions of this thing. Okay? So, oh no, this is so you want it to be moved up there? Yeah, so remember, this is supposed to converge to something which is close to the mean, not to the mode, right? So this is the mode, and the mean is actually shifted down there. So we'll actually talk about this. All right, so, okay, so what are the convergence guarantees? So in fact, the convergence guarantees are going to drop off straight up from the convergence guarantees that we have for Wasserstein gradient flows, because the subspace of Gaussians is totally geodesics, right? Geodesics between two, Wasserstein geodesics between two Gaussians stay Gaussian. And so it's a very nice space to work with. And so what we expect essentially is that PT is going to converge to this argmin, right? Since pi is the projection of, is tracking this process, it should go to the closest Gaussian to pi somehow. So let's see when this could be the case. So what you can do is write those first order conditions for this minimization problem. And you see if you start staring at this, so I'm not expecting you to do this. So those are the first order conditions that you actually get. And those first order optimality conditions, which were derived using, those can be done in any geometry you want. So they were just done by Euclidean gradients. And you can see that it's not always going to be the case that it converges to what you want. You start to need to impose some properties on V, on grad V and on Hessian of V essentially for this to reach some unique minimizer somehow. All right, so what kind of conditions can we get? Well, we're going to go with probably the strongest of all, strong convexity. And so we have this folklore results that says that V is alpha strongly convex if and only if the KL functional on the space of on the Wasserstein space is alpha strongly convex in a geodesic sense. Right, so this is a classical result. This is the basis for the famous Lotz-Dorn-Bellani result, for example. And so, if we assume that V is strongly convex, we have this. But what we get from just the fact that Gaussians is a totally geodesic subset is that it's also alpha strongly convex when I actually look at Buras Wasserstein space, because the geodesics here are the same as the geodesics there. Right? Positive. That's right. It's a constant in front of the Hessian. The Hessian is lower bounded by alpha times identity. Thank you. Yeah. So yeah, alpha big means more convex. Okay. So once we have this, which will be evident from the next slide. So once we have this, we can actually get exponential contraction in squared Wasserstein distance. All right. So you start at P naught, and you're going to get e to the minus 2 alpha contraction when alpha is positive. You also get exponential contraction in the objective value. All right, so your objective value is going to converge to the minimizer exponentially fast. And even if you're not strongly convex but just convex, you can actually modify a little bit your objective function and show that, of course, you're not going to get, there's no unique minimizer in that case. So you're going to get convergence in objective function, and it's going to be at a slower rate, 1 over t. But by combining the two objectives like Wasserstein squared and KL in your Lyapunov function, you can actually get some non-trivial convergence results. I'm going to skip quickly through this. If you do not like cubature rules and Runge-Kutta and you think I've cheated you and that I should address the accuracy of those rules, you can actually write a vanilla stochastic gradient descent, right? Because here you have expectations. So you could actually just do gradient steps, replacing the expectation and using off-the-shelf results for stochastic gradient descent. You're going to get some standard guarantees for this, which actually look like some guarantees that were provided by Alki and Rigollet in the context of logistic regression with some ad hoc reparametrization for the covariance matrix. So I don't want to spend too much time. I want to switch gears now. And for the last part of my talk, I'd like to actually discuss the statistical properties, right? So we know how. We know we're going to get to this argmin, and the question is this argmin any good, all right? So clearly, this is something I should have done before, but I was so eager to work on gradient flows that I didn't care. And so this is how it goes, all right? So remember, this is our target, right? So now I'm going to care only about the centrality parameter, this Bayes estimator, the average of pi. And my estimator for it obviously is going to be the average of pi hat. And the question I'm asking is how close is the average of pi hat, to the average of pi? Okay? So that's going to be a natural statistical question. If that's my target and I'm doing this, how good is it? And I'm going to obviously compare this with what I would get with Laplace, which is the mean a posteriori, the max a posteriori, the max of pi. All right? So those are the two things I'd want to look at. So to be able to say something like this, I need a scaling somehow, right? If it's just pi is e to the minus v, I mean, those are all constants. I mean, they're all going to be constants away from each other, and I certainly don't have the math to tell you sharply what the constants are. But in stats, those v scales with the sample size, which we like to think of as being large. Right, so let's look back again at the logistic regression case. It's the sum over n things that are all of order 1, basically. And so essentially, I can think of v of b as being of order n, and I'm going to write it simply as n times v of beta. All right? And it's actually a general statement. You can always think of your posterior on n observations as being n times a function. And so it's going to be e to the minus n times v. All right? So that's the scaling I'm going to get, and I'm going to try to see how close I am as n become big. All right? How close those things are. So the first thing we want to look at is, think of v as being now order 1. So it means think of this as being some quadratic potential, for example. Then what's going to happen is that this will look like the variance of my 1 over n will be the variance of this distribution. All right, so if I draw a point at random from my posterior, it's going to be essentially 1 over root n away from this mean a posteriori I'm looking for. All right, so the benchmark, being stupid, just sample 1 point at random, and it's going to be 1 over root n away. Can we do better? So it turns out that for the Laplace method, it actually does better. All right, so it's a good idea to go get this maximum a posteriori. So rather than being 1 root n away, you're actually 1 over n away, and there's an optimal scaling in the dimension that's fairly well known by now. A good place to look at it is Pocoini's paper, where he assumes that this v is strongly convex, and this more recent paper by colleagues at MIT actually extended it to the case where v is not strongly convex, because as we know, the Laplace method really only requires that you have one global maximum, and the n is going to squash exponentially down every other competitor. And so really, it's going to look like a Gaussian no matter what it is. But it's going, obviously, v is not strongly convex. It's going to be hard for you computationally to find this minimizer. But the result still holds for the global minimizer of v. Okay, so that's the benchmark. Think of it as 1 over n. Let's forget about the dimension dependence right now. It's a little messy, so I don't want to actually get into this. All right, so I'm going to try to, as the best I can, to walk you through how we would actually analyze the distance of the mean of pi hat to the mean of pi, my target. So the first thing is I'm going to actually define this alternate potential v bar, which is n times v, but now I basically rescale everything with sigma hat and mu bar and mu hat, okay? And the scaling here, if you do a simple change of variables, which I write here, so just trust me that it's simple, and it says that the expectation of this random variable that's drawn from a distribution that has this potential, right, this rescaled potential, is basically what I'm looking for rescaled by 1 over the standard deviation, right? So it's actually really the quantity I want to control. How far is mu hat from m pi actually properly renormalized by the scaling of mu hat itself? Okay, and actually the sigma hat will be of order 1 over n, and so this will be essentially root n times what I'm looking for. Okay, so I do this rescaling, so I'm interested in the expectation of this x bar that has this potential. So let's look again at the first order optimality conditions and what they're actually telling me. Those first order optimality conditions, they look pretty mysterious like this, but in fact, they're telling me something which is really amazing. So it's telling me that the expectation of grad v of this guy is 0. The expectation of a Hessian of v is 1 over n times sigma, essentially, and z here is just the standard Gaussian. So I'm going to move in 1D, so I don't have to deal with dimension. And basically, if I do the change of variable v to v bar, right? So look at what's here. This was precisely v bar. There was no n, but here I have the n. I put it here, and that's also v bar. And so essentially, it's telling me that v bar prime in expectation is 0, and v bar prime prime of Gaussian is also equal to 1. Anyone knows what this is telling me about v? So it's something that has to do with the Hermite expansion of V. All right, so the Hermite expansion is really about expectations of the derivative of a function evaluated at a Gaussian. So this is what it is, right? V bar, I'm going to write its Hermite expansion. So those are the probabilist Hermite polynomials. So the first one is identically equal to 1. Then I have a linear polynomial. Then I have x squared minus 1. And if you look at the coefficients in this expansion up to the 1 over k factorial, they're actually, so they're just really the expectation of V bar against this basis. But by using Gaussian integration by parts, you can actually show that this is really the expectation of the kth derivative of V bar. So if I go back here, this is really telling me that the first coefficient in this Hermite expansion is equal to 0, and the second coefficient is equal to 0. So if I write my expansion with the first, second, and third, I'm going to have that V bar is really just a constant plus a Gaussian potential plus a remainder term that's of third order. And so now that's going to make my life quite easier, because what it's telling me is that this expectation of x bar, which is really m bar minus pi mu hat over sigma hat, is this expectation against e to the minus this third order potential here. So now I do a little hand waving, and you have to trust me that doing some tedious calculation, you end up by showing that this thing is of order 1 over n to the 3 halves, because now I'm at the third order. And everything is expanding with like the small parameter is 1 over root n. It's really the standard deviation of my thing. All right, so sigma hat is 1 over root n. And so what I get is that m pi minus mu hat divided by something of order 1 over root n is 1 over n to the 3 halves. So if I push the 1 over root n on the other side, I get n to the 1 over n squared here. Whereas I had only 1 over n. So the standard thing where you just draw a point at random is 1 over root n. Laplace does better, gives you 1 over n, and that's not surprising that people have been using this. It's actually a good idea to do this, but it turns out that this variational inference is actually an order of magnitude better. So the result that we have is the following. So if I assume, so here I try to not, but at the same time do. So I want to emphasize the fact that for this result to hold, we don't need V to be strongly convex. However, we need V to be strongly convex to run the algorithm, etc. But just those conditions, which tell me that things are basically well behaved, can be replaced by strong convexity of V. All right. So if you're willing to assume that V is strongly convex, then all these things go. Just assume V is C4 and strongly convex. Then what you're going to get, I need C4 because I'm going to third order and I need to control the remainder term. Now I'm no longer one-dimensional. That's the full theorem. So in higher dimension, we actually get d to the 3 halves over n to the 3 half. And that's for the rescaled one. So since I know the scaling is of order 1 over root n, I can actually, for the operator norm, I can actually put it on the other side, and I get this weird scaling d to the 9 halves divided by n to the 2. Yeah. All right, and it's actually tight. Okay, so since we actually keep track quite a bit, right? So if you look at the things we have to control, this stuff here, we actually know all the way down, so we can actually produce a function for which it's going to happen. Yeah. Sharp, yeah. So you cannot improve the dependence in those parameters. Okay, so, I still have a few minutes. So the question you may ask is, what happens if you're not log concave, right? So if you have a bimodal distribution, in this case, it might be a terrible idea to actually try to use one Gaussian. And in fact, this is clearly not the closest Gaussian, right? The closest Gaussian should cover both modes here, and it's certainly not. And that's because the landscape is non-convex, is going to get trapped in some local minimum, and it just doesn't work. And so what do you do here? Well, here we actually propose to use mixtures of Gaussians instead. So try to find a mixture of Gaussians that's the closest to the target. And the way we do this is by thinking of a mixture of Gaussian as being a measure on the parameters mu and sigma. So here, this is the density of a Gaussian with mean mm sigma. And then we actually just take a measure on those guys, all right? So this is a measure on Buras-Wasserstein, on the parameters of a Gaussian. And now we're going to do a Wasserstein gradient flow for mu. Okay, so this is a Wasserstein over Buras-Wasserstein. All right, so it's a little brutal, but it's actually not, we're not the first ones to think about this. People have mostly thought about this for finite mixtures, but actually for continuous mixture, this actually gives you a really nice and clean analysis of what's going on, because you can think completely mean field in that case. And And so we're just going to run this. So now you see the functional we're looking at is mu maps to the KL of P indexed by mu. Okay, so it's a bit of a complicated functional. It's nowhere near geodesically convex. Okay, this thing is a nightmare. In fact, there's multiple parameterization that will give you exactly the same P mu. So and those spaces are non-convex. So there's no result here. However, something very satisfactory for me, who tends to actually study things like least squares or completely obvious algorithms. For this guy, I actually did not know what the algorithm was going to look like, and I just started writing autocalculus and seeing what the gradient flow would look like. It ends up looking like this. So each Gaussian now, so I'm going to start with a finite number of particles, each being a Gaussian. So I have a bunch of particles on the Buras-Wasserstein space. So think of it as a particle methods where the particles are actually Gaussian, right? And so I have more particles on this Buras-Wasserstein space, and each of them is a mean and a covariance, and they evolve by interacting with other means and covariances through this P mu t, where mu t is really this discrete measure, right? So it's this finite mixtures of Gaussians. And so they're interacting through this potential. So it's kind of subtle, but because you don't see any J on the right-hand side, but it is an interacting particle system. They're really interacting with everyone. And this thing actually allows us to get some nice results, all right? So we over-parameterize it. So think of having 4 modes. You start with a bunch of Gaussians there. Each of those particles evolves by interacting with the other ones, and you reconstruct something that kind of looks like this. All right, so this is great, and we could stop here. The problem is, if you actually screw up your initialization, you see this mode is the biggest, this one's the second biggest, and look, those weights are totally screwed up. And the reason is because when you start with a uniform mixture of Gaussians, you end up with a uniform mixture of Gaussians the whole way. And so you have to move all these particles across the space just to recreate the mass. And if you started with a lot here, they have to all move to the bottom right to actually create that mass. And there's just energy barriers that they cannot cross. And so what is the answer? Well, I mean, both Gabriel and Lénaïc would tell us you have to use what they call unbalanced transport, what other people would call Wasserstein-Fischer-Rao geometry, which actually moves the weights as well. And so you just basically write the Wasserstein gradient flow now in Fischer-Rao geometry. So you actually move also the weights on each of those particles. And now you have coupled system of 3 ODEs, mean, covariances, and weights. And this is what the Fischer-Rao gradient flow looks like for those weights. And now you can actually reweight those guys as you go, and you actually get some nicer results. They're not like perfect, but clearly they're much closer to reality than they were before. Okay, so I'm going to conclude here. So essentially, the Wasserstein geometry for variational inference is almost tailored to what we wanted to do. I mean, when I first saw this, they said, oh, we want to do this, and the objective is the KL of dot to your target measure. And I was like, well, I've seen that before many times, right? So those are one of the very few objective functions we actually understand from the perspective of geodesic convexity and gradient flows. So this is almost immediate probably for the most of the people to use this analysis for this problem. I thought what was surprising is that actually this closest Gaussian, the fact that you actually fit the variance gives you a much better estimate for what the mean actually is. This was actually quite surprising to me. Beating the Plas method by a full order of magnitude is quite impressive. I think this concept of Gaussian particles where we evolve discrete particles on the Buras-Wasserstein space is something that should probably have bearing to, well, anywhere where people use particle methods and approximate distributions by, finitely supported distribution. Well, they could use a mixture of Gaussians instead. Of course, you lose a lot, but in terms of proving results, but it's actually quite interesting, and it actually leverages, right? The Buras-Wasserstein space is a positively curved manifold. So as far as I'm concerned, this is the first real instantiation of optimal transport on a manifold that's actually useful, rather than just doing it for the fun of it and using RCD spaces. And then there's the variable weights, right? So here we use Wasserstein-Fischer-Rao, and if you look at Wasserstein-Fischer-Rao, I mean, if you come from reaction PDEs, it's completely natural. But if you actually come from the other way, you're like, okay, so I want to start making my weights move. You have the Fischer-Rao geometry, you stick it together with the Wasserstein geometry, and you just add the 2 metrics, and that's it. Well, you could take any metric on the weights that you want, right? Like you could take any Bregman divergence and like make a metric out of it, any Hessian metric you want, and you can just put it in there. And so my collaborators are experimenting, and there's some geometries that actually work better in practice. Obviously, this is totally out of my reach now because it's just like experimenting until we like to see the pictures. I'm never going to be able to prove a theorem saying one is better than the other. Right, and so what we're currently exploring is what happens like beyond Gaussians or mixtures of Gaussians, right? Like, if our goal at the end is to really compute this mean a posteriori of this guy, are there better distributions than Gaussians to beat even this 1 over n squared, right? All we care about is to estimate as accurately as we can the mean of pi. And so, you know, maybe a double exponential might actually do a better job for certain target measures. And so those are the things we're actually experimenting. So that's more of the why rather than the how for the last point. All right, so on this, I'm going to conclude, and thank you for your attention.
Thank you very much. And are there questions or comments? Please.
What does that space of measures look like? Like what do we know? Is there a characterization of what type of measures can be written down as an integral of these Gaussians?
Pretty much anything that has a smooth density, right? So basically what you're asking in, so this is a fancy way of asking what measures can be expressed as a continuous mixtures of Gaussians, and anything that has a C, I can assure you that anything that has a C infinity density will.
Even if it has compact support?
It doesn't have to have compact support.
No, but what if it does have compact support? Then it's hard to represent as a mixture of Gaussians, right?
Yeah, that's right, but I can approximate it arbitrarily well.
I see. Okay.
Other question, please.
You went quickly at the end, so you say you switch to an unbalanced optimal transport, and then you apply like the theorem of Lénaïc to show global convergence. Is that the idea?
No, I don't. There's no theorem that applies there.
Okay, why?
And the reason is because it's not. Oh, so you mean for Wasserstein-Fischer-Rao?
Yes, when you do the last flow, where
yeah. So we didn't prove anything for this part because that was really. I mean, you're welcome to do it. I don't think we're gonna do it, but it seems there's a progression, natural. It's like first do Wasserstein, let's do unbalanced transport, and then do Gromov-Wasserstein. It seems, but I won't. Yeah, I think it's going to go through just fine here. I mean, if you assume that V is strongly convex, you're going to get there. The thing is, if V is strongly convex, it's hard to justify the use of Wasserstein-Fischer-Rao geometry.
Why would you need it to be strongly convex? In Lénaïc's theory, there is no need for anything being strongly convex. I mean, just convergence, I mean.
Yes,
global convergence.
Oh, just convergence.
You want a rate. It's because you want a rate. Okay.
You mean if I make the kind of statement of like if this thing converges to something, it's going to be the global maximizer?
Yes, would be the first step, I guess.
Yeah.
Suspense.
Yeah, I think. Yeah, you can get something like this. Probably. Yeah, I'm not sure. I don't want to actually be put on record actually saying that this is possible. There's actually a lot of things that go really wrong there, so I'd have to think about it, and I haven't thought about it before.
Okay. Okay, there was another question over there.
Thank you very much. Very, very nice talk. So my question was about these Gaussian particles. So it seems to me that, you know, sometimes exactly as you explained in the beginning, when you do Langevin diffusion and you have to estimate this gradient log pi. So this final method is something which is very similar to this, where you are approximating pi as sum of, and so you have the explicit expression for this pi. So is there a way to generalize this in order to have, you know, so density reconstruction, and so you can do Wasserstein gradient flow for whatever functional entropy functional that you want.
Yeah, that's a good point. So I think it rejoins. It goes back to Andrew's first question, right? Which is, you know, what can you approximate using mixture of Gaussian? And if I actually, you know, one question that would be very legitimate there would be indeed if for a certain number of Gaussians, so for a mixture of a certain number of Gaussians, I can actually get, you know, absolutely close to grad log of anything I want. Then I actually almost get this Wasserstein gradient that I wanted. And you know, is there any explosion? Like, is there propagation of chaos? Is, like, you know, you could ask this kind of questions, right? So is it stable in terms of approximation, or does this thing completely blow up? So this is not something we've looked at, but those are very good questions, yes. So yeah, I don't know what the answer is, but yeah, that's definitely, I mean, I mentioned at the beginning kernel density estimator. This is literally a kernel, pi mu t that I was tracking down is literally a kernel density estimator.
Okay, so I don't see any other question, so we can thank again the speaker. Okay, so seems we are ready. Okay, so let me introduce the next speaker. She's Codina Cotar from London, UCL, and she will talk about next order asymptotics for optimal transport and endpoint configurations.
Thank you very much. Thank you very much. It's a great pleasure to be here at this workshop. It's all been very interesting talks so far. And also for me, it's very exciting to be in Pisa because it's my first time. So I'm looking forward to going tomorrow and having a picture supporting the tower. So, okay, so what I'm going to talk about, so some of it's work I've done before, but at the end there's also going to be some new work. So work I've done before is with Mita Petrakem, and I'm going to briefly talk about the optimal transport results. Then I will focus a lot more on the endpoint configurations results, and I want to parallel a bit how the proofs work, because even though it's quite similar results, the proofs are quite different in both situations. And then later on, I will discuss some new work which I'm just finishing with Manuel Gnan from Utrecht. And this new work is on log and some other nice formulas which involve the constant which appear in these asymptotics. Okay, so I'm going to be interested in an optimal transport problem with n equal marginals, and I will have the cost will be sum of Cxi minus xj, and for me the cost will be, for much of the talk, will be 1 over norm of x minus y to power s with s between 0 and d, and then at the end I will also take s to 0, and then I will have the cost will be minus log of norm of x minus y. Okay, so as we can see from these formulas, the cost that I'm looking at have so-called long-range interaction. That means everything interacts with everything else at long range, and this causes a problem to begin with, but we will see later on that you can reduce the long range interaction and transform it into a short range interaction, which allows to do lots of really nice things. Okay, so looking at a problem of this type, I'm not going to focus on the case with finite n. There's some really nice work done by a lot of people, some of them who are in the audience, like Butazo, De Pascale, Di Marino. So I'm not going to focus on this case. I'm just going to go straight to taking the large n limit. And the first thing you may want to do, you may want to understand what kind of convergence this has in the large n limit. And it turns out that I can divide by n to power 2, and then I will converge to something which you can define as an infinite margin optimal transport problem, and you can even compute explicitly, and it's this term which has the product measure in it, which turns out to be an optimizer for this infinite marginal optimal transport problem. And in physics, this is called a mean field. Okay, so then once you have something like this, you may want to understand whether you can quantify the speed of convergence. And it turns out you can. So then you are going to take from the n marginal optimal transfer problem, you are going to take this limit, and you are going to try to see if you can divide it by something appropriate, which will allow you to obtain another limit when n goes to infinity. And there are some results, partial results, which have been done, and one is this Lieb-Oxford bound, which is quite famous in the math physics and in the chemistry literature. And basically, what it says that if you divide by n to 1 plus s over d, you have a lower bound, which is universal, so it's just a constant depending on s and d, and this integral. And this was originally done in a paper by Lieb and Oxford. Trivially, we can also get an upper bound, so this is just by taking the product measure as a competitor for the optimal transfer problem. So then we see we have some bounds, and then we are going to ask ourselves the question, if we divide this quantity by n to 1 plus s over d, if you can find a limit. And it turns out that you can indeed find a limit. So this was done first by Simone Di Marino. He was the first to do it in dimension 1. Then there was a paper by Lewin Liebenzeiringer, where they looked at s is 1 and d equal 3, and they had some conditions on mu, and they used something called Graf-Schenker decomposition, and then we generalized it to any s between 0 and d, and for rho with somewhat more general assumptions via another decomposition, which is called Pfefferman-Gregg, and which was invented by Pfefferman in 1985, and he applied it for s is 1, d equals 3, and then his PhD student generalized it to some more cases, and then generalized it to all the cases, all these cases. Okay, so I will come back to this decomposition because it is a main tool for both these problems, and also I will come back at the end also when I discuss some other types of problems you could look at. Okay, so the results that all of these people got. So it basically you take optimal transport, take away the mean field limit, divide by n to 1 plus s over d, take n to infinity, and then you end up with a constant which depends just on s and d, and you have this integral. Now this difference in the physics literature is called exchange correlation energy, so that's why I've called it EXE in the top. Now the case when mu is just a uniform measure is called uniform electron graph and goes all the way back to Dirac. And one main problem that people are interested in is to find the exact value that this constant has. And this is still unknown, though there is a conjecture that it is approximately 1.4442. Okay, so the main tool that we have used is this Pfefferman-Gregg decomposition, which allows us to transform the long-range interaction that we have in the Riescots to something which is a short-range interaction. And as I said, it was introduced by Pfefferman, then extended by Gregg, and then we did a further extension. Basically, what it's saying, so I have the Riescost 1 over x1 minus x2 to the power s, and I'm going to transform it to a different cost, so it's this cost here, which is no longer as nice looking, but if we see what's happening in the integral, here I have interaction just between x1 and x2 in these a's, which are balls, in some ball packing f omega. So that means that the only interaction which I see here is short range, everything only that's happening in A. And then, of course, this is not the whole term. I have some other term, which is an error, and is this W, which is positive definite. And even more importantly, if I am going to look at the optimal transport problem with n marginals for this W, that is, and I'm going to take its corresponding mean field, and that's going to behave really nicely, and it's going to go away, it's going to disappear when n goes to infinity and m goes to infinity. And here m is the number, so I have m type of balls with radii r1 up to rm. And so m is the number of ball types of radii. Okay, so this is what helps us. So transform a long-range problem into a short-range program, which is a lot easier to work with. Here, I would also like to add that this kind of decomposition is not unusual in the statistics mechanic literature. So there's people like David Bridges and Roland Bauerschmidt, who are the kings of finite range decompositions, and they have developed other types of finite range decompositions which would not work for us, but they work in the case of problems from probability and statistical mechanics, such as the phi-4 field and other such models that appear in there. So there's other types of decompositions that exist where you have long range and you transform it into short range, plus some error which is controllable. Okay, so another type of result that we got at the time. So we wanted to understand even more this the behavior of this exchange correlation energy. So we obtained something that we called small oscillations. So we took any two of these EXE for n and n tilde, where n tilde is smaller. We divided it by the appropriate n and respective n tilde to 1 plus s over d, and then we wanted to see how the difference behaved. And it turns out that you can quantify it. You have some constant, it's bounded by some constant divided by log to n tilde. So you can improve this constant. So if you work, for example, with a Coulomb cost, you can get a bound of order n tilde. But for us, because we were working over the whole range, we only got this log to n tilde. Now, one thing I would like to mention is that in this paper, we did not obtain this inequality exactly for the EXC. We obtained it for a somewhat different problem, which is, so it's not an n marginal optimal transport problem. Is a so-called grand canonical problem, which was more amenable to such computations. However, it turns out it's not necessary to work with a grand canonical problem for any of the purposes in this talk. So you later on, when we started working with the endpoint configurations, we also tried to use this grand canonical formulation, and we got stuck when we tried to do this large n limit. We got stuck, so then we had to find alternative ways, and we found alternative ways, and then it turns out you don't need to worry about this grand canonical formulation for what we do here, and everything I say works for the n marginal optimal transport. As a side note, there's some very nice work which was done on the grand canonical problem by people like De Pascale and Di Marino. But as I said, I'm not going into it because for us it turns out not to really matter. Okay, so some consequences of small oscillations. So if you look at the exchange correlation of n to 1 plus s over d, and you call this fs of n, this turns out to converge as n goes to infinity uniformly with respect to s. And this will have quite a lot of implications regarding some limits I will show you at the end. So it will allow us to do a lot of really nice things, such a statement. Okay, so now I move on to the second model that I'm looking at, and this is the endpoint configuration, to which this Gellium model is the first one of them. So I take n electrons, and I take a neutralizing background in a domain omega, which is of size n, and I'm going to look at a quantity of these states. So I have the sum of 1 over norm xi minus xj to power s, minus this integral, plus the mean field, and I'm going to minimize over xi in omega. So a priori, this minimization was done over xi in omega in a paper in 75 by Lieb and Naenhofer. And they were able to prove so looking at s equal d minus 2. They were able to show that if I divide by n, this object has a limit, and it's equal to some constant, which I'm going to call minus E gel S, just from Gellium model. And in just looking at this particular model, we generalized it in 2019 just for S between D-2 and D. Okay, so here the minimization was over xi in omega. However, you can show that for S between D-2 and D, you don't need to specify that you minimize over xi in omega. So you can just say, I'm going to just minimize over all xi, and then you can show that the minimizer will stay in omega. So this just for S between D-2 and D. To show such a statement for S smaller than D-2 is an open problem, and nobody knows how to do it. Sorry? So I mean, at the moment here, I can just take it some omega, some box, but later on you can take general. So here, in this first slide, it's just I'm just going to say I can just take a 0 n to d or something like that, 0 n to 1. It's just something nice, just renormalized. Yes. There are some assumptions. I don't know exactly all the assumptions, but there will be some assumptions. Yeah, and I didn't memorize them, but they are. Okay, so then, so this was just the case. If you look here, this is just a uniform measure, yeah? So uniform measure, we scaled to the fact that this is of size n. And you can define the problem more generally, and you can take mu in some general probability measure with some density with compact support. So we have taken it with compact support for technical reasons to show various existences and things like that. So, and you can minimize over xi in RD. So you do this minimization for this more general case. And again, you can try to understand if the limit exists. So here, if we look, the difference between this slide and the one before is that I have rescaled. So here I had the size is n. Here the size is no longer n, so this is why I have these extra terms here. It's just a rescaling procedure, so they are equivalent via n to s over d difference. And you can try to understand whether there is such a limit exists, and it turns out that we can show that such a limit exists, and it's this constant which depends just on s and d, and this integral. I will get to the proofs in a bit. I'm just going to tell you the results, and that I will try to tell you a bit about the proofs, how they work. Then there is yet another problem, which is the minimum energy point configuration, Coulomb and risk gases. And this problem is stated it has similarities with the Gellium model. So I have sum of 1 over norm xi minus xj to s, plus n sum of V of xi, where V is a confining potential growing at infinity. And you have the cases, so for S between 0 and D, you have the risk gases, S is 0, so this is the log, the D-2 is the Coulomb, and S greater than D is the short range interactions. And of course, when you take S to infinity, you have the best packing problem. And this problem has been extensively studied by people like Sandier, Serfati, Gougerie, and they try to look at, again, they did the same thing as for these other two models. So they looked at the next order term, and they try to understand what this next order term is. And I'm just going to state the result. So suppose I have mu v is a minimizer of these quantities, and then you can show, so they have some assumptions on V, so there are some assumptions on V, some technical assumptions that you have on V, and if this rho V, the density is smooth enough, then you can also show that you have an next order limit, which looks just like the next order limits of the other two models that I discussed. And there's another constant here, which I'm calling C gas. Okay, and this was done in various work. So it was done for S between d minus 2 and d. And also it was done for the log in dimension 2 before. And then Mitja Petak and myself, so we used a version of this Pfefferman-Gregg decomposition to extend it to all the S between 0 and d minus 2. Not the log, because the Pfefferman-Gregg decomposition that we had breaks down for the log. So we didn't do the log. Okay, so let me tell you now a bit about how these proofs work. So just to contrast them. So we want to transform a long-range interaction into a short-range interaction. So this helps for the lower bound. You have two bounds, an upper bound and a lower bound. Yeah? And we are trying to get them to match. For the upper bound, for the optimal transport problem, turns out to be relatively easy because you have some sort of subadditivity argument. So if I take a mixture measure, so suppose I take a measure which is alpha mu1 plus alpha mu2, then I can look, I can show that, so I can look, so I can split the optimal transport problem for mu into the respective optimal transport problems for these mu1 and mu2. Obviously, I pay the price by having n alpha 1 and n alpha 2 in these exchange correlation terms. And that comes up as an upper bound, and it allows quite easily to obtain an upper bound which looks like this. Now for the lower bound, what you would like is to do the same. Yes? You'd like to transform the original optimal transport problem into to bound it by some of other optimal transport problems on some smaller ends. So you want to split the measure, and you want to also split the n. And this is not, you cannot do that for this 1 over norm of x1 minus x2, but turns out that once you reduce the problem to an optimal transport one on this short range interaction, you can do it. So, and you can reduce it quite nicely to the sum of optimal transport problems, and then things work out. Okay, so then we want to do the same for these Gellium models and for the minimum energy point configurations. And I will actually focus on the Gellium model because the point configurations model will come for free. So we won't actually need to do any work for that model. Okay, so what we want to do, again, we want to get an upper bound and a lower bound. And the problem comes, surprisingly, in the upper bound. So the upper bound, you can no longer get such a nice subadditivity. If I'm just looking at the case when I'm looking at a uniform on the unit box on 0, 1 to d, then you can do it. But once you move away from the unit box, you cannot do it. And why can you not do it? Because here you will have mixed terms coming to play also. What do I mean by mixed terms? So for the optimal transport problem, if I have this mixed measure alpha mu1 and plus alpha 1 mu1 plus alpha 2 mu2, and I was defining the corresponding optimal transport problem, I would take the minimizer of these, and I would construct a competitor for the original problem. And you can try to do the same for the Gellium model. However, there will be some terms now which will not cancel. If you are in the case where S is between d minus 2 and d, you have some things to help you. So you know that the minimizer lives in support of the measure, and that's something which helps. And something else that you know is that you have separation of points. So what does it mean? That if I have any minimizer point, and any points xi and xj in the minimizer are bounded from below by some constant which does not depend on n. So that also helps. So if you are between d minus 2 and d, you can still do things. However, once you go to S smaller than d minus 2, this is not possible anymore. as I said, we do not know whether the minimizer stays in the support of the marginal, and we also cannot prove a separation of points, and we tried very hard. So then we were quite a bit stuck for a while, but then it turns out that if you work with a short range decomposition, so if you work with this one or that one, you can prove things. So you can prove that the minimizer stays in the support. You can show that you have the separation of points holds, and this helps you in the end obtain some sort of subadditivity argument in order to get the upper bound. For the lower bound, also for the lower bound, we also have to work a bit harder, because we as I said, we tried originally to use this grand canonical formula, the equivalent of the grand canonical formulation, and we got stuck, but then it turned out we could bypass it nicely, and we didn't have to work with it. We again used the properties of the minimizer for the short range interaction, and we were able to transform them nicely to the original problem. So this is very briefly how the problem works how the solution works for this Gellium problem. Okay, so another term that I want to introduce is the periodized Gellium energy. So basically, here, if I am going to call this one E, and Kr is this omega, and X is any configuration. So I'm going to take any configuration, any endpoint configuration in this Kr1, and then I'm going to repeat it in the smaller cubes, where I have split the bigger cube in this smaller cube. And I also put another condition, so I put a barycenter equal to 0 condition, and I'm going to take all these limits. So I'm going to have some the R is going to infinity, and the R1 is going to infinity, and then I'm going to call this C period per ST. And I'm introducing this now because when I'm going to try and compare the constants between these different problems, this is the quantity that will allow me to say something about how these constants behave with respect to one another. Okay, so you define this quantity. You can also show that the limit exists. Okay, so then let me go to the comparison and tell you a bit about what is easily seen. So you can easily see that you have the Gellium one is a lower bound for these exchange correlation energy coming from optimal transport, even more. So if I have, so this is the optimal transport one, this is the endpoint configuration, and Gellium one. So this is actually the relationship between them. And if I am for S between D minus 2 and D, I can show even more things, because these two will actually be equal for finite m. If I go to S smaller than D minus 2, then, well, they may or may not be equal. But okay, so then you look at them and you try to understand what happens when you divide by the relevant n1 plus S over D, and you want to understand how these constants behave with respect to one another. Okay, so then what happens? So to begin with, we had this argument which was just holding for S between D minus 2 and D, and we showed that the constants for these three problems were the same. And then we extended it also to include the D minus 2 case. And there was also another proof a bit later by Lewin, Lieb, and Seinger. So using the same strategy as us, but with a better competitor, and they also showed this for D minus 2. But then it turns out that you have this equality for all S between 0 and D. And I'm just gonna tell you a bit about how the proof goes. And I'm giving you the proof that we originally have, because it turns out that this is actually the only proof that you need, though we didn't realize this at the time. Okay, so the main idea that we had originally was to reduce the Gellium minimization and to work with the Gellium problem of a periodic configuration. So we could show that if we look at this problem, that this constant was equal to the one of the Gellium. So we could show that for S between D-2 and D. And then we try to construct a competitor for the optimal transport problem using this minimizer from the periodic problem. And you can construct this competitor. We constructed it, so it's not quite the right type of competitor, because you construct it not exactly for the original exchange correlation problem, but you construct it for one with a somewhat slightly different marginal, but that turns out not to be the problem when you take n to infinity, because when you take n to infinity, they become equal. And so this is how we did it for S between D-2 and D, but without D-2. And then, so our competitor was not really good enough for D-2, which is why we couldn't originally do it. And later on, we did it by using continuity. So we were able to show that the constant from the optimal transfer problem is continuous. And actually, you can even show some nice limit when S goes to 0. And basically, the only thing that we still had to do for this problem was to show that the constant, that this Gellium constant was continuous when S was going to D-2. And we were able to do this in 2019. Okay, as I said, there was another, so there was the paper by Lewin, Lieb, and Seiginger, where they used same type of idea, but they had a better competitor, and their competitor worked for D-2. And then also in the same paper that they had, they also tried to see what would happen for S smaller than D-2, but the argument doesn't quite work anymore for them, and they then try to compare the optimal transfer problem with a somewhat different Gellium problem. So they looked at some version of CPER where they had to add some additional constraints, but there's no justification why this other problem, this other periodic constant with additional constraints, is the problem can be equated to the original CGEL. So this is how it was done. But then, while we were working on this next order term for the M-point configurations, and we were trying to bring it down to for S between 0 and D, we realized that all you need to know is the short-range interaction. So if instead of looking at the general problem, so instead of looking at the original problems, if I look at the optimal transport problem with this cost, and if I look at the Gellium problem also with this cost, and if I try to compare the constants, so I can do next order term for these two short range interactions. I get some constants which will also depend on M, and then somehow magically, if I look at these short range interactions, I apply exactly this argument that we had in 2017. We have equality for these constants of the short range problems. Equality for all S between 0 and D. So then all you have to do, you have to show that when you're going to take this m to infinity from this short-range interaction, that will converge to the correct C-gallium, and it will also converge to the correct CUEG. And actually, you can show this quite easily, because if I take, for example, CUEG, that is an upper bound for the short-range problem, and then you can show using this. You can bound it again from below, but by the original long-range interaction. So you sandwich in between, and they become equal when m goes to infinity. So it turns out that the original argument would have worked if it just looked a bit better. So then you have this equality for the constants for all s between 0 and d. Okay, so this is what you have. Now, of course, we didn't do the s equals 0 because our Pfefferman-Gregg decomposition doesn't work for s equal to 0. So you could try and devise a decomposition which works for s equal 0, but it turns out that it is not enough. So that it is not needed. So because you can use limiting results in a careful way, and you can use small oscillation type arguments to go to the s equals 0 case, and to show that even for s equals 0 for all d greater or equal than 1, you have this next order term, both for the optimal transport problem and also for the endpoint configuration. As I mentioned before, for the endpoint configuration, the log in d equal to was already done. Okay, so you can do this, and then again you can also ask, once you have this, and then this is work with Manuel Mann that we are trying to wrap up now. Now, of course, once you have these next order constants for the log, so I called it C log, CUEG log, and CGel log, then again you can ask the same kind of question as we were asking before. What happens to these constants? Are they equal or are they not? And you can try to go via the same approach as here to try and do competitors and to try and construct competitors, but then it turns out you don't need to, because we have these magical type expressions in which you can show that when you take appropriate limits, these constants for the rest converge to the constant for the log. So then, just because we had shown these constants to be equal, we get the equality for the log constants. Now, another thing that I didn't put here on the slide is that we can also show, and again in this paper, we can also show, if you look at these CUEG constants and the CGel constants, and if you take left and right derivatives, we also have some formulas for them. They are not very pretty, which is why I didn't put them there, but you have some explicit formula for these derivatives. Now, I can't say I know why they would be useful for, but anyway, they exist, and well, you have some such formulas for the left and right derivatives. Okay, so I would like to end by telling you about some things, maybe briefly about things that I would like to look at next. So as I mentioned, so this kind of decomposition is quite known in statistical mechanics, and they also have some such decompositions which work on manifolds. And my dream, or what I'm trying to do next, what I will try to do next, is to look at these problems. So in particular, I will at these problems on manifolds, and for at least for the Gellium problem, there is a long-standing open problem where they're trying to look at the next order term on the sphere. So there's people like Saf and Hardin who have worked extensively on trying to understand what's happening at the next order on the sphere, and so far the only known result is a result in d equal 2 for the log, where there is a paper by Bettermin and Sandier, and they were able to get the next order term for the problem on the sphere. And the way they did it, they managed to transform it, in this case, into the kind of problem that Sandier and Safati were working on, and this way they were able to get the next order term. But the method breaks down outside the log, so the result only holds for the log, and outside it's an open problem. So I will like to stop here. Thank you.
Thank you for this talk. Other questions? Yeah, please.
And the packing constant of NRD. What is the relation between the constant which depend on S?
Slightly deaf, sorry, I'm sorry to say.
Sorry. The constant depend on S, is sure or not? There is a dependence on S of the constant, but
yeah, there is a dependence on S. Yeah.
It is proved, but it's a
change.
There
is a dependence on S. Yeah.
Okay, and is there a relation with the packing constant in RD?
So I mean, the packing constant corresponds to the S going to infinity.
To infinity. Okay. And when S tends to 0, it goes to...
S goes to 0, it's just the log. It's just a log problem. Yeah, it's just...
Okay, but
I mean, and there you have problems. You have this crystallization conjecture. Yeah, the Abrikosov crystallization conjecture, and that's which is still open. Yeah, I mean, it's been done in dimensions 8 and 24 by Vyazovskaya and collaborators, but it's still open.
But it is the same for the packing constant, là. The dimension 8 and...
yeah.
Is exactly the same problem.
Yes.
Okay.
Yeah. Sorry? Oh yes, I did flash a slide because I thought I was running out of time. But there is, okay, so let me, so there is, so here, so this is, yeah, so this is where you have the crystallization conjecture in dimension 2. There's also a conjecture in D equals 3, where the minimizer has different behavior depending on what values S has. And again, in high dimension, everything is anecdotal, so nobody knows what's happening apart for D equal 8 and 24. And in D equal 3, there is this conjecture that all these constants should be 1.4442. So I mean, there are some simulations, but there is no. I mean, I think some people. I mean, I discussed over the summer with staff and Hardin. I don't think there is a specific. Nobody said, "Oh, it's gonna go this way." I mean, I can't. I mean, this basically just conjectures mostly. Yeah. I mean, I think basically outside of these dimensions. I mean, maybe 5, 6, 7, anything that's not. Yes.
Okay, there are other questions there?
Yeah, thank you. So my question is about this last thing that you say about.
To talk louder, sorry.
Yeah, about this last thing that you said about the spheres.
Yes.
So, what kind of interaction do you put? So it's the distance in Rn, the geodesic distance, or something that has to do with the Coulomb potential. So you solve the Laplacian equal to 0.
Sorry, I have to come.
Yeah, sorry.
I'm very sorry.
No, I was saying it's more so the interaction that you put between 2 points is like the distance. So the geodetic distance has some power, or is the solution, the fundamental solution of the Laplacian?
No, you the power. Yes, you can.
Okay, power law.
Yeah.
Okay. Of the geodesic distance or the distance in Rn?
I mean,
so the sphere is in Rn, right? So
yes, I mean,
side,
you can. Yeah. I mean, at the moment, yeah, I'm just gonna do some. I'm gonna try.
Okay.
I mean, there's more than one way they define some of these things. Yeah. Yeah.
Okay. Are there more questions? Okay. So if not, we thank the speaker again. And okay, so now we have the coffee break and we resume at 4:30. Okay, so let us start the second part of the afternoon session. Let me introduce Mattia Magnabosco, who comes from Bonn, University of Bonn. He will talk about the Brunn-Minkowski inequality and its relation with the CD condition. Please.
Thank you very much for the introduction, and thank you also to the organizer for inviting me here. The topic of this talk is exactly this, the title, so the Brunn-Minkowski inequality and its relation with the CD condition. And the results I'm going to present are obtained in a joint work with Lorenzo Portinale and Tommaso Rossi. So let me start very quickly by, oh, this doesn't really work. On, okay, should work, okay. So this is the CD condition, which was pioneered by Lotz, Sturm, and Villani, and it's basically generalization to the setting of metric measure spaces of the notion of having a lower Ricci curvature bound and an upper bound on the dimension. And this is a definition which is done with the optimal transport, as you will see. So we have two constants, k and n. K will represent the lower bound on the curvature, and n will represent the upper bound on the dimension. And a metric measure space XDM is said to be CDKN if for every pair of absolutely continuous measures, mu0 and mu1, there exists a Wasserstein geodesic eta, which connects them, and for which this entropy convexity inequality holds for every n prime greater than or equal than n, and for every time n0, 1. So this is actually an entropy convexity inequality, because if you put a minus sign at the left-hand side and so also at the right-hand side, and you change the sign of this inequality, you obtain at the left-hand side the Rényi entropy, and at the right-hand side you obtain a suitable convex interpolation between the Rényi entropies of mu0 and ρ0, which is done accordingly to this optimal transport plan pi and with these coefficients tau kn. I'm not really interested in commenting really the value of this coefficient, but let's just say that they come from Riemannian geometry, and in some sense they are the right one. Meaning, in particular, they are the right one according to this result, which is the fundamental result of, above this condition, let's say. And this is the result, so let's take a weighted Riemannian manifold, so M manifold of dimension n with the distance induced by the metric tensor. And let's take as a reference measure with this measure, so the volume measure multiplied by this drift of this type. Let's say that V is C2. And this metric measure space is a CDKN space if and only if the modified Ricci curvature bound, which takes into account also the drift given by V, is greater than or equal than K times the metric tensor G. So basically, in the setting where we are able to define a Ricci curvature tensor, so the setting of weighted Riemannian manifolds, this Ricci curvature bound is equivalent to this condition, which now doesn't really involve the differential structure. So in the setting of metric measure spaces, we can actually take this metric measure condition as the definition of lower Ricci curvature bound. So this was the introduction of the CD condition, and one of the main merits of the CD condition is that it's actually sufficient to deduce some functional and geometrical inequalities that hold in the smooth setting also for these metric measure spaces. And one of them is the Brunn-Minkowski inequality. And right now I'm actually proving the Brunn-Minkowski inequality directly, because actually the proof is quite simple. And also I will need some steps of the proof in the following of the talk. So let's start from this, which is the entropy convexity inequality given by the CD condition. And then we want to apply this entropy convexity inequality to two special measures. So let's take two sets, A and B, which have positive and finite measure. And we take these two measures, mu0 and mu1. which are the renormalized and restricted measures with respect to A and B, so defined in this way. And now if we want to evaluate the right-hand side with these two measures, we end up with this quantity where we have actually substituted the densities, which are 1 over m of A and 1 over m of B. We substituted them to rho 0 and rho 1. And so the right-hand side is exactly this quantity. And now we want to go further with the estimate of this right-hand side. And to do so, we introduce this quantity, theta IB, which is actually defined in different ways depending on the curvature parameter k, but I don't want to comment a lot about it. Let's say that this is the right definition to have this estimate. So basically with this choice of theta AB, we can estimate this integral with this version of the integral, where we are evaluating the tau coefficients just in theta AB. So now this is not really an integral anymore because the integral doesn't depend on x and y. So since pi is a probability measure now, we actually end up with this quantity, which is basically a convex interpolation in some way of these measures to this power 1 over n prime. So this was the estimate on the right-hand side. Let's keep this in mind. And we now want to estimate the left-hand side, and we can do it with Jensen's inequality. And in order to be as clear as possible, I've actually rewritten this integral in this way. So you may easily notice that I can actually limit myself of integrating on the support of mu t, because outside this rho t is 0, so the integrand is 0. And we can also divide and multiply by this quantity m measure of the support of mu t. And this is done because now inside the parentheses we have a probability measure, because on the support this is a probability measure because we are renormalizing it. And now then we can apply Jensen's inequality and end up with this quantity where now the exponent is outside the integral. Right? But now this integral is pretty easy because the density rho t is a probability density with respect to m, because it's the density of mu t. And so this integral is 1, the integral just with respect to m, and we have this normalization, and so we end up with this quantity right here, with this, the exponent that we also have at the right-hand side in particular. And then there is this one last step, which involves this set of t midpoints that it's basically this set depends only on t and a and b, and it's the set of all points that can be obtained as t midpoint of a geodesic that starts in A and ends in B. So defining the set of t midpoints in this way, it's a fairly easy consequence of the structure of optimal transport geodesic, that this support is contained in this set of t midpoints. And so this inequality is completely trivial, and we have also estimated the left-hand side. So with both these estimates in mind, we can actually end up by combining those two and also the starting entropy convexity inequality, and end up with the generalized version of the Brunn-Minkowski inequality, which is this one. So in particular, it's an estimate of the measure of the t midpoints right power with this convex combination of measure of the starting set and the ending set. So of course this was just a computation, but this inequality holds for every t in 0, 1 and for every n prime greater than or equal than n accordingly to the CD condition. And so basically we have proven this inequality for every choice of these two parameters. So we basically end up with this condition. I've stated this condition accordingly to the notation of the CD condition because it's strictly related as we will see in the following. So as before, given k and n, we say that a metric measure space supports the Brunn-Minkowski inequality, and we call it BMKN. If for every pair of Borel sets now with positive mass, this inequality that we have just proven is true for every choice of n prime greater than or equal than n, and for every choice of the time in 0, 1. So what we have just proven in the computation in the last slide is that the CD condition implies the Brunn-Minkowski inequality. So it's in some sense natural to ask about the converse implication. So if the Brunn-Minkowski inequality is actually enough to deduce the CD condition. And of course, this is a natural question because in mathematics, equivalences are better than implications. But also, there is another important thing about this possible equivalence that, in my opinion, is the most important part about this question. And it is that if we are able to prove this equivalence, we can actually characterize the CDKN condition of the curvature dimension bound with a property that now doesn't involve optimal transport anymore. Because as you may notice, then this formulation is not related to optimal transport because we are just taking the set of T midpoints, which is no way related to optimal transport. So this equivalence would be nice also for this reason, to provide another characterization without invoking optimal transport at all. So this is the question, and unfortunately we don't have a result in full generality about this, but we have two partial results that maybe are of interest. And the first result is actually the equivalence result in weighted Riemannian manifolds. So let's take as before a weighted Riemannian manifold in this way. And what we were able to prove is that if this weighted Riemannian manifold supports the Brunn-Minkowski inequality, then the Ricci bound, this Ricci bound holds. And therefore, since this is equivalent to the CD condition, also the CD condition holds. And so the conditions are equivalent in this setting. And the reason why I have stated the result in this way is to emphasize that actually in our proof, we really use that, we really pass to this Ricci bound. So we are actually able to prove this Ricci bound starting from the Brunn-Minkowski, but we don't really have a direct proof of Brunn-Minkowski to CD. So this is in some sense indirect, and it uses the Ricci bound, so the differential structure really. So of course this is maybe a nice result in weighted Riemannian manifold, but if you're working with the CD condition, you really want some metric results, because in some sense the CD condition has really a huge importance when you're dealing with metric measure spaces and not with Riemannian manifolds where you already have this Ricci bound. So it would be nice to have a result also in the setting of metric measure spaces. And in fact, we don't have the full equivalence result in this setting, but we have a weaker statement that I'm going to present. But before doing it, I want to go back a little bit to this slide in particular and make you notice that in doing this estimate, we could have just stopped before introducing the set M of t, and we could have just stopped by considering the estimate with this measure of the support of mu t. So the computation are exactly the same, and we end up with the same estimates, except that we can substitute the measure of the support here instead of the measure of the midpoints. So what happens is that this other inequality is in some sense stronger, but of course it makes sense because it's also it also follows from the CD condition. So from this observation, there's actually, it comes directly this definition, which is what we call strong Brunn-Minkowski inequality. So as before, we have the two parameters, and we say that the metric measure space XDM supports the strong Brunn-Minkowski inequality, SBMKN, if for every pair now of Borel sets with positive and finite measure, there exists a Wasserstein geodesic eta, which connects these two normalized measures, such that this inequality now with the support instead of the set of midpoints holds for every n prime greater than or equal than n and for every time in 0, 1. So following the observation I was doing before, in the previous slide we actually proved that the CD condition not only implies the Brunn-Minkowski inequality, but it also implies this strong version of the Brunn-Minkowski inequality. And actually, what we were able to prove is that the equivalence between these two conditions holds in a wide generality, let's say. In fact, for every essentially non-branching metric measure space, the CD condition is actually equivalent to the Brunn-Minkowski inequality. So this is, of course, a result which is quite general, but regarding the motivation about the problem that I was mentioning before, this is not perfect. Because As you can notice, now we have an equivalence with the CD condition, but now the strong Brunn-Minkowski inequality still involves optimal transport in some sense. So optimal transport is not at the right-hand side because this is completely free, but it's still at the left-hand side because we have this eta, which is an optimal transport geodesic, basically. And with this last remark, I want you to justify this statement that I'm going to make, that this definition, this condition still depends on optimal transport, but not too much. For sure, not as the CD condition. So this is the remark. It's very easy to prove that in essentially non-branching metric measure spaces, where the Brunn-Minkowski holds, and also if the strong Brunn-Minkowski holds, the geodesic eta connecting these two normalized measures is actually unique. So in particular, also this support is unique. And now this support only depends on A, B, and T now. And so we can really call it dt of AB. So now this dt is not the same as MT. It's not the set of all T midpoints, but in some sense it is the set of all midpoints which are in some sense highlighted by the optimal transport interpolation. So with this notation, we can actually write this inequality in this form. And now this inequality is still depending on optimal transport, for sure, because this set is, but it's basically as the same form of the Brunn-Minkowski inequality. So this is basically the part of the result. And now I want to finish the talk with some observation in general about this whole problem, starting with the differences between strong Brunn-Minkowski and Brunn-Minkowski. So with a little recap, what we were able to prove is that in essentially non-branching metric measure spaces, the CD condition is equivalent to the strong Brunn-Minkowski inequality, which of course implies the Brunn-Minkowski inequality. So in order to close this chain of equivalences, we would like to understand better the relation between the Brunn-Minkowski and its stronger version. So I'm trying to make you understand a little bit what's going on with this picture. So this is a very easy example. So let's say we are in R2 with the Euclidean distance and Lebesgue measure. And we take now these two sets, A as this rectangle and B as the union of these two squares. So if you want to evaluate this, the set B1 alpha and M1 alpha, which are the one characterizing BM and SBM, you can do it very easily in this situation because the optimal transport sends the upper square here in the upper square of B and the lower square of A in the lower square of B. So the set D1 alpha of AB is none other than the union of these two loose squares. While if you want to evaluate the set M1 alpha, you also have to consider, for example, geodesic that starts from the upper part and goes to the lower part because it's the set of all T midpoints. So the set M1 alpha, of course, contains D1 alpha, as it's a general fact, but it also contains these two red rectangles. So it's strictly bigger also in this very, very easy example. So this shows that also in very easy examples, these two inequalities are in some sense estimating the mass of two very different sets. But at the end of the day, R2 is a weighted Riemannian manifold in particular, so these two conditions are equivalent. So what is really going on? The point is actually very simple, and it is that we are asking, of course, the inequality on the set for every pair of sets. So in the right part of the figure, I'm actually giving an heuristic explanation why in this setting, for example, you can understand why the Brunn-Minkowski inequality can imply the strong Brunn-Minkowski inequality. And the reason is very simple because you can basically partition A in A1, A2, B in B1, B2 in this way. And now you can simply notice that for this pair of sets, so A1, B1 and A2, B2, the sets DT and MT are actually the same. And so if we basically have the Brunn-Minkowski inequality, we can apply it to this pair and this pair, obtain an estimate on this measure and this measure, and then summing them up, we will end up with a measure on the set which is the union of these two, which is exactly D1 alpha of AB, which is now the set characterizing the strong Brunn-Minkowski though. So this was a little bit of a heuristic, it's not exactly what's going on, but this shows two things. the first thing is that maybe a partition argument is really helpful in understanding a little bit better this problem. And the second thing is that actually, in general, it could be very useful to understand better the structure of the optimal transport, because the partition we did here is exactly in these two sets, and this line is exactly the set where the optimal transport map is not continuous, as you can notice by the figure. So this was regarding the difference between strong Brunn-Minkowski and Brunn-Minkowski. And just two last final comments. The first one is that proving the equivalence between Brunn-Minkowski and CD could provide also an alternative proof of the globalization theorem for the CD condition, which was proven originally by Cavalletti and Millman. And in fact, this was proven by Cavalletti and Mondino that the local version of the CD condition actually implies the Brunn-Minkowski inequality in its global and unique version. And the second comment is the relation between the measure contraction property. And it's actually very easy to prove that for essentially non-branching metric measure spaces, the Brunn-Minkowski inequality implies the measure contraction property. And in general, the measure contraction property is strictly weaker than the Brunn-Minkowski inequality also in the setting of weighted Riemannian manifolds. In fact, it's possible to construct a space which is MCP-Kn, but which doesn't satisfy the Brunn-Minkowski inequalities with the same constants. So in some sense, the Brunn-Minkowski inequality is much closer to the CD condition than the measure contraction property is, and in some sense there is some hope to actually close this equivalence and finishing what this whole talk was about. So with this, I thank you for your attention, and that's it.
Other questions, comments? Please.
Yes.
So in the definition of strong Brunn-Minkowski, you're only saying that there exists at least one W2 geodesic that has this property? But
yes.
Once you assume that the space is essentially non-branching, then you know that there is only one.
Yes, exactly.
So I recall, so that if you assume the strong CDKN property, right, which is that you say that every Wasserstein geodesic is geodesically convex, then this also implies that your space is essentially non-branching.
Yes.
So have you could write down like a very strong Brunn-Minkowski where every geodesic satisfies this condition. Would you expect that the same would be true?
Yes, I mean, in the end, it's basically the same, because also if you ask for every geodesic, basically here you're just asking for one, and then a posteriori you have this geodesic is unique. So basically you have it already for all. So also if this existence definition, you end up having one single geodesic connecting these two measures. So you basically have the inequality for all geodesics. So it's not really a difference in essentially non-branching metric measure spaces. Of course, if branching is possible, it could be very different, but of course, also a lot of other techniques that we've used are not really available in non-branching spaces. So,
right, I guess I just mean, so the issue, right, is that the strong CDK condition implies essential non-branching.
Yes.
So I was wondering if you thought about whether a strong, like a very strong Brunn-Minkowski would also imply essential non-branching.
Yeah. Okay. This is okay. Okay. The proof of what the result you were mentioning is quite tough in general. So it's quite long. So probably it's possible to do it just assuming strong Brunn-Minkowski, but I'm not completely sure about it.
Okay. Thanks.
Okay, so if there are no more questions, we thank the speaker again. Okay, so let me introduce next speaker, who is Nicolò De Ponti. He comes from CISA, and he will talk about from reverse Poincaré inequalities to bounds on Controvich distances. Please.
Okay, thank you, and thank you also to the organizers for inviting me. So yes, today I want to present some inequalities involving Kantorovich-Wasserstein distances, but the focus will be not really on the result, but on the proof of these results, which is based on each semigroup techniques. And also I want to highlight the role of these reverse Poincare inequalities that I will present in a moment. Let me just sketch the setting of my talk, which is the one of RCDK infinity space. I don't want to give a precise definition. Maybe I only comment a bit the difference between this setting and the previous setting of the talk of Mattia. Here I add an error, so we are RCD, not CD. This means that the each semigroup associated to the space is linear. And also this allows to give a definition of the curvature bound that we have on the space in terms of the each semigroup. And so the information of the curvature that I need to do all the computation is this Bakry-Emery bound. Then the other difference is that I have an infinite here, which means that I have no upper bound on the dimension of the space, and so all the inequalities that we will see are dimension-free inequalities. Of course, in this class of spaces, we still have no smooth spaces. This introduces some technicalities that I'll hide here. If you want, for my talk, you can think that we are working with weighted Riemannian manifolds with weighted Ricci bounded by K. Okay, now, what is the reverse Poincare inequality? You can. Yes. Okay, by a very classical interpolation argument using the each semigroup and using our bound on the curvature, you easily deduce this inequality, and this is the reverse Poincare inequality of order Q. If you want, Q is the power appearing here and here. And okay, RK is a time factor, explicit, and I will use this inequality in two ways. The first one, okay, we neglect the negative term and take the L infinity norm. If you do this, you obtain a quantitative L infinity to Lipschitz property, which means that if we start with an L infinity function f, at positive time, the each semigroup is a Lipschitz function, and also we have a quantitative bound on the Lipschitz constant of ht of f. In the final part of the talk, we will see other inequalities appearing that, again, we deduce easily from this Poincare inequality. And if you want, we can call this reverse Poincare inequality of power q. Notice that we deduce by taking the power q divided by 2 here, and then we must use the Jensen inequality to obtain this inequality. Of course, using Jensen, we need convexity, and this reflects on the fact that here q must be bigger or equal than 2. Okay, now for the first part, I will focus on this inequality, and we will see what can be deduced by this. I promise some results on Wasserstein distance. What is the connection? It is easy. At least, yes. No, for the moment, no. All in one result, I will need k bigger or equal than 0, but this. It can be negative. K, if k is here, this is 2t. You interpret it in the limit, and k can be negative also. Okay. Okay, what is the connection with Kantorovich-Wasserstein distance? At least with Kantorovich-Wasserstein distance of order 1, it is easy. If you recall that Wasserstein one distance can be obtained in duality with Lipschitz function, and also the L1 norm can be obtained in duality with the L infinity norm by a simple duality argument from the L infinity to Lipschitz property. You deduce a bound on between Wasserstein 1 and the L1 norm of the evolution of the function f with the heat flow. This is really easy, but can be already used to obtain something interesting. If we plug in this inequality an eigenfunction of the Laplacian, notice that ht of an eigenfunction is explicit, and we can deduce a lower bound of the Wasserstein one distance between the positive part and the negative part of an eigenfunction. This is related to a conjecture of Steinerberger, who conjecture both a lower bound and an upper bound with this rate in terms of the eigenvalue of this quantity. I'll come back in a moment of why I came up with this conjecture. Let me say that on smooth Riemannian compact Riemannian manifold, the upper bound is also known. Upper bound, I mean in terms of the same quantities, just by changing the constant. And also the lower bound has been proved with very different techniques by Mukarege, and he needs to prove in his approach fine properties of the eigenfunctions to have these results, while here we need almost nothing about the eigenfunction except this triviality. Okay, another inequality that I will present is an indeterminacy estimate involving Wasserstein one distance and this new term. Here f is not an eigenfunction, is a general L infinity function if you want. These quantities should be interpreted as the size of the zero set of a function. Here we are in great generality, so we have no information on the regularity of the zero set, so we just use the perimeter of the set where f is positive. And this inequality can be proved. I write in the lower bound this term in this way, because there were previous contributions on this inequality by various authors. In some of them, the exponent here is bigger than 1, so the inequality is not sharp, because it's known that the exponent 1 here is the best possible. Also, Cavalletti and Farinelli, after many attempts, obtaining the same inequality, so with the sharp exponent, but with very different techniques, not involving each semigroup. Here I propose a simple proof using the each semigroup. And the first inequality is the one that we have already seen. I just write ht of f in this way because I want to use this trivial bound and obtaining this, using also the fact that the semigroup is mass preserving. Then to continue the inequalities, we need to have an upper bound of this term. Noticing that for the moment we have no perimeter term. Y perimeter is connected with the each semigroup. It is connected by this inequality that can be deduced again using each semigroup techniques. You take a general L infinity function with an L infinity norm less or equal than 1. Okay, here in the first equality, I just using the definition of heat flow. And then the Laplacian and the heat flow also in this general space are self-adjoint, so you can do integration by parts and obtain this equality, sorry. And then if you know the L infinity to Lipschitz property, we can bound this, and so passing, if you want, to the limit using ZF, more or less the characteristic function of a set, you obtain this inequality for every set A. And then refining a bit this estimate, you can prove that this quantity is bounded from above by this term. And now, again, you have a general inequality for all t, you optimize in time, and the proof finishes. Why one studies these quantities? So Wasserstein one between positive and negative part of a function, and the indeterminacy estimate, because one is interested in computing the size of the zero set of a function, and in particular of an eigenfunction. This is related at least on a compact Riemannian manifold on a very famous conjecture of Yau, who conjectured these two bounds. Now, the lower bound is known on a smooth Riemannian manifold by a very important result of Logunov. Since the problem is very interesting, of course, one tries to study also variants of the problem, and here maybe I highlight the interest of studying the same problem on no-smooth spaces, and following the approach of Steinerberger, who firstly introduced these inequalities on the indeterminacy estimate. Cavalletto and Farinelli notices that using the indeterminacy estimate, which is valid for L infinity function, and in particular you can apply it to eigenfunction. And if you know an upper bound on the Wasserstein one distance between eigenfunction, and they proved this upper bound with this logarithmic factor here, which is non-optimal. I say before that for smooth Riemannian manifold, you know that you can remove this logarithmic term. On no smooth spaces, we don't know, but probably you can remove, but we don't know how to do this. Anyway, at least if you use this inequality, you put together the two bounds and you obtain a lower bound on the size of the zero set, again interpreted as the perimeter of where the eigenfunction is positive. Of course, this is very far away from the sharp bound, but at least it says something. And let me notice that using ideas of our proof that I showed before, we can also remove the logarithmic function without using any upper bound on the Wasserstein distance, but reasoning directly with the ideas of the previous proof, we can remove the logarithmic function, and in particular obtaining a better bound. Some comments on this. Okay, in this lower bound, it appears an L infinity norm and L1 norm of the eigenfunction. If you have an upper bound on the dimension, but also on no smooth spaces, there are inequalities involving L infinity and L1 norm of the eigenfunction, and so you also obtain a lower bound in terms only on power of the eigenvalue. Again, very far away from the sharp one, but it's something. And also another small remark is that all the results that I present up to now really requires only an linear Hith semigroup and an L infinity to Lipschitz property. This is interesting because there are some nice structures, in particular some sub-Riemannian structures and also some fractal spaces that are not RCD K infinity, but satisfies this assumption, and so also all the results that I present. Now, in the final part of the talk, I use the other inequality that we have seen at the start of the talk. Let me give some motivation. I'll present now a result of Louise and Savarin that should be interpreted as an Eiger or the Eiger generalization of Eiger, I mean, where we use here the Wasserstein P distance instead of the Wasserstein 1 distance. Of the first results that I present, I have presented between Wasserstein 1 distance and L1 norm. Here we put Wasserstein P distance and Ellinger P distance. Ellinger distance are defined in this way of the evolution by the heat flow of the two measures. This is, as I said, the result of Louise Savarin, which is valid only for P between 1 and 2, at least in their statement. Why this limitation? And I want to focus on this limitation because the proof is based on, if you want, two things. A variational characterization of the Wasserstein distance and the Ellinger distances. The one with Wasserstein distances, I think, is well known here, is in terms of Hamilton-Jacobi subsolution, if you want. For Ellinger distances, they prove a characterization in terms of an even simpler ODE. Here, no gradient, only a simple ODE. And then also you have variational characterization. The proof is picking a competitor for the Ellinger distance and show that the evolution by the heat flow of that competitor is a competitor for Wasserstein. For doing this, they need to use a reverse Poincare inequality with power Q. And as I show at the start of the seminar, it is known only for Q bigger or equal than 2, and this reflects with the fact that P, which is the conjugate exponent, is less or equal than 2. A different result of Ledoux here, which is a sort of Sobolev-Kantarovich inequality. I will not say anything on the result, but again, the proof is based on 8 semigroup techniques, and with an expression, you can notice that the crucial bound is this one that is needed, and Ledoux obtained it as a consequence of reverse Poincare inequality, and again it has the same limitation, which reflects on the fact that here P is less than 2. Now, the natural question is it possible to remove the limitation P less or equal than 2? Okay, for the Ledoux result, you can do this, as noticed by Bogachev, Shaposhnikov, and Wang, if you have at disposal LP bounds on the square root of minus Laplacian, and you have this bound if you work at least on smooth weighted Riemannian manifolds. But if you want to work on RCD spaces, up to now these bounds are not known. Moreover, if you want also to extend the results of Louise and Savarin, you really need a pointwise inequality. Notice sorry, that here, if you want, is an integral inequality, so an inequality between LQ norms. But in the result of Louise and Savary, you really need a pointwise inequality. And so we propose a way to bypass this problem with the new each semigroup inequalities that we prove with Farinelli and Tamanini, which is valid on RCD K infinity space for every K, so negative. And this is the inequality. We propose the name reverse Beckner inequality because standard Beckner inequalities are a family of interpolation inequalities between Poincaré and log Sobolev. Here, our inequalities interpolate between reverse Poincaré, so if Q is equal to 2, this is exactly the reverse Poincaré inequality that I presented at the start of the seminar. When Q is equal to 1 in the limit, you recover the reverse log Sobolev. And also, you can prove this inequality really using only its semigroup techniques. So also, we are not going away from the general framework of using each semigroup to prove this kind of inequalities. And okay, I conclude here. Thank you for your attention.
Thank you for the talk. Other questions or comments? Giuseppe, please.
These last inequalities, you are able to improve the regularization estimate from Wasserstein to Hellinger?
Yes,
range of the regularization estimate.
Yes, exactly. Yes, the idea, I didn't write the results, but the point that also you have this inequality, you can immediately use it to improve the result of Ledoux removing this limitation, and also your results between Wasserstein and Hellinger removing this limitation. So you obtain the whole family of inequalities for every P.
Thank you. Are there other questions? Okay, so if not, we thank again the speaker. Okay, so our next speaker is Giacomo Enrico Sodini. Okay, Giacomo. Yes, you ready? Yeah, he will talk about a relaxation approach to optimal transport with applications to the unbalanced case. Okay, please.
Okay, thank you. I don't know why there is this transition. Anyway, so thank you, and thank you to the organizers for inviting me. So I will present a few results we obtained in collaboration with Giuseppe Savary related to the unbalanced optimal transport. So first of all, I will start from a new perspective we have obtained in the classical optimal transport setting, and then I will use this perspective to give a new definition for a class of costs in the unbalanced case. So in the classical case, so supposed to have in general two spaces. Here these are Polish, and we have the space of the vector spaces of real valued measures mx and my on the spaces, and I will endow these spaces with the narrow topology, so the topology in duality with continuous and bounded functions. So once you have a cost function on the product space, you can immediately give a notion of cost between measures, which we call singular cost. So you take two measures. If they are Dirac masses with the same non-negative mass, you prescribe the cost to be their mass times the cost of moving the point on which the first one is concentrated to the second point, and plus infinity in all other cases. So this cost is basically plus infinity always. What we want to do is to compare this cost with the classical optimal transport cost, best to say an extension of this cost by linearity, in the sense that you take two measures, mu and nu. If they are non-negative and they have the same mass, then you compute the classical optimal transport functional, and you set it equal to plus infinity in all other cases. So if you restrict this functional to the product space of probability measures, you obtain precisely the optimal transport cost. already from these two definitions, you can see that this second function is lower semi-continuous and convex. And if you compute the classical optimal transport cost on pairs of this kind, so m delta x, m delta y, you obtain precisely the same value that the singular costs give to this pair. So we have two functions. One is convex and lower semi-continuous, and another function that stays always above it. The result that we expect and we obtain is that if the cost function is C is proper and lower semi-continuous, then the convex and lower semi-continuous envelope of the singular cost is the optimal transport cost. So the new thing is this one. So the possibility to express the optimal transport cost as the convex and lower semi-continuous envelope of a simple object. And this equality is, of course, well known, is the Kantorovich duality, but I am putting it here because it will be useful to recall it later, and also because when proving this first equality, this is just a byproduct of the proof of this part, and it is a very, very simple proof. So this result provides at the same time an immediate proof of the Kantorovich duality and a nice representation of the optimal transport cost, and I will try to convince you that it is also a useful representation because I will use it for the unbalanced case. So now the unbalanced case, so we are not the first one to deal with this kind of problems. There has been dynamical formulations of the optimal transport cost in which you take like a Benamou-Brenier formulation of the optimal transport problem, and you put some source term taking into account the loss or gain of mass, static formulation of the problem, in which you, in some cases, you think to have some point at infinity to which you can send or receive mass from, and the most recent approach are the one given by Liero, Milk, and Savarin, Chizat, Peyré, Schmitzer, and Vialard, which are the so-called entropy transport costs, which are connected to what I'm going to present. So, as I was saying, in the classical case, we wanted to, first of all, give a cost between delta measures, and the way to represent delta measures in the balance case is simply to identify delta measures with points in the space. In the unbalanced case, we want to identify weighted Dirac masses, and there is a slight representation issue due to the fact that the zero measure can be represented in many ways as a discrete measure, because you can take any point and zero mass and you still obtain the zero measure. So the right space to represent weighted Dirac masses is not really the product space of weight and position, but rather the so-called geometric cone on the space, in which you take the product space that I was saying, and you quotient it with respect to the obvious equivalence relation that sends all the pairs with the same zero mass to the same point, the so-called vertex of the cone. There is also a topology on the geometric cone, but I will not describe it into details. So now we have the right object, and we can define a notion of cost function, which will be used to measure how much we pay to move a weighted Dirac mass from one weighted Dirac mass to the other. And the hypotheses we take on this function are, one is very natural, so to ask that the function is proper and lower semi-continuous, because minimization problems will be involved. And the other one, so we ask to this function that if we fix x and y, and we look at the map sending r and s, so the weight to the function computing the arguments, this function must be convex and one homogeneous. So these are both technical assumptions in the sense that they're useful when you want to prove stuff. And they also have like a modelistic interpretation in the sense that, for example, we are saying that if you move double of the mass, you pay double, which is reasonable. So examples of these functions, a very simple one can be given by the product of a function taking into account weights and a function taking into account the space. And this is an example of a function that appears here. And the second example, which is slightly more involved, but is interesting because it was considered in the work of Liero, Milk, and Savarin, and it is connected with the Hellinger-Kantorovich distance. So it is based on the use of what is called a marginal perspective function, which is generated by entropy functions. So you start from entropy functions and the cost function, and there exists a procedure to produce a function h as the one I was presenting before. And so I will not describe this procedure, just to say that the class of costs they consider is contained in the one that I will present. And a special example is the one given by the Hellinger-Kantorovich distance, which is realized in this way. So if the spaces are the same, you fix a distance on the space. If you take as entropy the 1 power entropy, and you take it as cost function this one, then the marginal perspective function they induce is this one, and the cost between measures that I will then connect to this function will be the Ellinger-Kantorovich distance. Okay, so now we have our function on points, on the geometric cones, and the singular cost, the unbalanced one, is clear, no? So you have two measures, mu and nu. If they are weighted deltas in 2 points, this time you can also allow to have different weight. Then you prescribe the cost to be the function in the arguments, and plus infinity in all other cases. Of course, this time we do not have a primal formulation of the problem, or at least not yet, to compare this function with. But doing precisely the same computation you do when proving the convex relaxation representation of the classical optimal transport cost, you obtain already a dual representation for the convex and lower semi-continuous envelope of this object. So this is given by the supremum. You see here the same function that you have in the classical optimal transport theory, but on a different set of potential. This time, instead of constraining the sum of the potential to be less than the cost function, you have the weighted sum of the potential less than the cost function h. And then, of course, now we have a convex relaxation formulation, a sort of dual formulation. What is missing in the picture is a primal formulation for the cost. And a way to see it is that in the classical case, the relation between dual formulation, primal formulation, and constraints that you have in the dual formulation is contained here. So here you have the dual functional, and here you have the, and then you're able to express the dual functional as the sum of the potential against any plan, the plans that appear in the primal formulation. And this object, the sum of the plans, is the object that is constrained to be less of the cost. And here, instead of having just the sum of the potential, we have the weighted sum of the potentials. So this time, the plans that we will have to consider will not be compatible just with the sum of the potential, but rather with the weighted sum of the potentials. So the plans will be measures on the product cone, such that if you compute the dual function, so if you do the integral of phi the mu plus the integral of psi the nu, you obtain the integral against the plan of the weighted sum of the potentials. And once you have a class of plans and you have your cost function, the primal formulation easily follows. And let me just remark that this relation can also be expressed in terms of what are called homogeneous marginals, but R and S. These are the variables on the cone. We have 4 variables. So X, R, Y, and S. Okay, so now we have primal, dual, and convex relaxation formulation, and the result we expect is that they are equivalent, and indeed they are. So if the cost function h is admissible in the sense that I told you before, then for every pairs of measures mu and nu non-negative, you can find an optimal transport plan in the sense just explained, and you have equality between primal formulation, convex relaxation formulation, and dual formulation. So now we have a kind of primal dual machinery that we have in the classical theory. So now I will present a few results that you can expect that can be generalized from the classical theory to the unbalanced case. So the first one is related to optimality conditions. So you know that in the classical case, the crucial concept is the one of cyclical monotonicity of the support of a plan. In this case, it will still be a crucial concept, but this time we will deal with the so-called convex cone generated by the support of the plan. So let me just give you the relevant definition. So if you have a subset in the product cone, the convex cone generated by this subset is built as follows. So you fix the space variable x and y, so you obtain like a slice of this set, and you take the convex cone of the slice and you attach all the slides. And the concept of cyclical monotonicity is basically the same. So you have a finite family of points in the product cone inside some set, and you say that is h cyclically monotone if the cost for this family of points is better than any cost you obtain permuting the points. And the result, again, is similar to the classical case. If you have 2 non-negative measures and you have a plan alpha which is optimal with finite cost, then it is concentrated on a set whose convex cone is h cyclically monotone. And also the converse is true in the sense that if if the plan is concentrated on a set whose convex cone is H cyclically monotone, then under some additional technical assumption I will list in a moment, then the plan is optimal, it has finite cost, and you can find maximizing pairs of dual potentials. And so the message should be that, okay, we have necessary and sufficient conditions for optimality, which are given by the cyclical monotonicity. Of course, there are these technical assumptions I was mentioning. So the first one is similar to what happens in the classical case. So we have to impose some finiteness of the integrals of the cost function. And the other two conditions are instead specific to the unbalanced case. And one is imposing that the convex cone of the set gamma is contained in the domain of the function, that the domain of the cost function is independent of the space variables. This means that if you have 2 points x and y, and you can move some r mass to some s mass, then you should be able to do it for all other points in the space. So move r mass to s mass. And finally, the last condition is related to the existence of some point in the interior of the domain of some subdifferential of the function h. So I don't want to enter into too many details. The point is that under some assumptions that are listed here, you can obtain also the converse implication. So second result, we should generalize what happens in the classical case is the metrical and topological properties of the cost. So if the cost h, besides being admissible in our setting, is also the pth power of a distance on the cone, compatible with the cone topology, then the cost you obtain on measures is again the pth power of a distance. Of course, if the cost is not uniformly bounded, you have to restrict yourself to a smaller set, but this happens also in the classical case. You have to impose some constraint on the moments of the measures. And the topology is compatible with a narrow topology. So the convergence with respect to the distance is equivalent to narrow convergence plus convergence of the moment. And okay, let me just mention that these partially generalize some results that were already contained in the work of Lénaïc and Savary related to the Ellinger-Kantorowicz distance, and that examples of cost functions h that are distances on the cone are already contained in the work of Nicolò De Ponti, and such functions were also used then by De Ponti and Mondino to produce distances between metric measure spaces with different total mass. Final result I want to present you is the one related to the existence of optimal transport maps. So here I'm presenting a very restrictive framework, so there are a lot of hypotheses, but also the cost function h is rather general, so we can expect it. So if the space is a compact and convex set in Rd with an unit interior, and the function is Lipschitz and differentiable, you have some twist condition on the derivative of the cost function h, plus the measure mu is absolutely continuous with respect to the Lebesgue measure, then you get the existence of a Borel map that it's an optimal transport map in this setting. So this means that it is a map from the space to the cone on the space, such that if you do the push forward the map of the initial measure, you obtain a measure on the cone, then you take the second homogeneous marginals of the measure, and you obtain the target measure. And if you compute the cost in the transport map, you obtain the optimal cost. And as I was saying, there are a lot of hypotheses, but also because the cost function h is pretty general. And for example, in the latest work of Lénaïc and Savary, you can see that they obtain better results for the Ellinger-Kantorowicz distance. And final remarks are the following. So maybe this convexification procedure can prove to be useful also in other contexts. So for example, if you want to treat the case of vector valued measures, or even maybe matrix valued measures. And it could be interesting to study also a bit deeper the geometric properties of the resulting metric space. So for example, I didn't say anything about separability or the geodesics into this space, but something has already been done by Giuseppe and collaborators in the work of this year. And finally, the use of this cost for applications could be also interesting, for example, for PDEs, where you have also some reaction terms, so you have gain or loss of mass. And this is everything, and I thank you for your attention.
Talk. other questions or comments? Okay, so it doesn't seem the case. So we thank the speaker again, and we thank all the speakers of the afternoon.